2021. Today in session number 9, we have with us respected Dr. Debasis Samanta sir, Professor Triple IIT Kharagpur. Welcome sir. Good morning, good morning sir.
Good morning. Good morning, Nidhi. Good morning.
Good. Okay. Sir,
Am I
can
audible?
you can...
Nidhi,
Yes,
am
sir,
I
you are
audible?
audible. Yes, sir, you
Okay.
are audible, sir.
Okay, thank you.
Okay. Sir, please share your PPT.
Sure. Okay. Good morning, everybody. Okay, video is available.
Yes, sir, video is available, sir.
Okay, good. So we are synced.
Uh, Excuse me, sir. If you want to start the session, you can start, sir. Participant will join.
Yeah, I think let's wait for another maybe 2 minutes, right?
Okay, sir. Fine, sir.
So Maybe we can start little bit 5 minutes late, but I will be able to compensate it.
Okay, sir. जी.
Okay, let the other people join.
Yes, sir.
Hello, Nidhi.
Yes, sir.
Yeah, I think we have 10 minutes late, right? Now you just decide whether we should start.
Yes, sir, you can go ahead.
Okay, fine. So let's start, right?
Yes, sir.
So good morning, all of you.
Good morning, sir.
Yeah. So I hope all of you, your family members, are healthy, safe, and doing well. So this is really a difficult situation we are going through. Only the thing that we can do is that we can keep ourselves safe, and that is the only way we can fight with the demo. Now, let's come to my presentation. So, as you know, today's topic is support vector machine and its application to machine learning. Essentially, support vector machine is a machine learning technique which was invented from now today around 30 years back. But still, the technique is one of the most robust and highly accurate technique. So that is why without learning support vector machine, you will not be able to learn machine learning properly. Now, before starting my presentation, I want to mention one important quotation. It is from Ian Goodfellow. Possibly you know his name. He is a pioneering author of the book Deep Learning, and he also has invented many AI algorithms. So he is a famous person in the field. So once he told, if you don't know machine learning, deep learning, and AI, then in coming 3 years, you will be treated as dinosaur. You know what it does mean. So you have to be extinct. And this quotation is particularly very much important for not only the students, but also for the teachers. This is because teachers should know machine learning concept so that he can teach his or her students more mature way. If you don't know machine learning, then you will not be able to decide what kind of problem that you can think for your student to carry out their project or research. So knowing the machine learning, this is very important. And on top of that, the support vector machine is also very much significant in this regard. Now give me the permission to off my video because video will take some bandwidth that can be saved, and then I will share my screen so that I can start my presentation. Possibly you know that my presentation include two sessions. In the first session, I will cover linear SVM, and in the second session, the advanced version of the SVM, it is called the nonlinear SVM. So there are two phases of SVM, linear and nonlinear. So the two things will be covered. Now let me off my video and then I'm going to share my screen. Any one of you please confirm if you can see my screen.
Yes, sir, it is visible, sir.
Okay, good. It is visible now. That's fine. So we can start. I was talking about support vector machine, and it is the one technique by which we can classify data. Now you know there are some computational intelligence technique is required solving few specific type of problems. One problem is called classification, also it is called prediction. Another technique is clustering, And then third technique is also there. It is related to the information mining. Most precisely, it is called association rule mining. Now, the support vector machine is used for prediction or classification. Not only this prediction and classification, the support vector machine also will be used for regression analysis and ranking. So regression analysis and ranking are the two machine learning tasks. Now, so with the one weapon, we will be able to hit three things: classification, regression, and ranking. But in this session, we will mainly limit to classification technique only, because regression and then ranking, our time will not permit, because we have to wrap up within 3 hours, out of which we have already started 10 minutes late. So now let's start. So in this presentation, in 2 sessions, I will first introduce yourself to the support vector machine. Now this introduction is required, assuming that my participants, they don't know anything about this SVM. So considering the 0 prerequisites, so that faculty members, research scholars or students from any discipline can take this lesson from me. Of course, in order to understand the concept, a little bit mathematics is required. And that mathematics is actually, at the very elementary level. So mainly the geometrical concept, like coordinate geometry, little bit idea, little bit differentiation, and some simple algebra that is required. So far the mathematics is concerned, we know that we all teachers, students, research scholars in the engineering domain should have that basic mathematics concept. Anyway, so I will introduce the concept of SVM. And SVM is all about, called the maximum margin hyperplane concept. So what is the concept of maximum margin hyperplane? That will be elaborated with examples. Then my session will come to the core discussion, as I already told. So my discussion includes 2 parts: linear SVM and non-linear SVM. So the internal things of the 2 SVM mechanism will be discussed in this session. So let us start about introduction to SVM. Now, if you see, the name is very peculiar. Name is called support, vector, and machine. Now, before going to start our discussion, okay, I will be here in the slides for 1 minute. So you don't think that I'm not moving the slides. So I just want to tell about what the 3 words mean to us. So first, let us start with machine. What it does mean? A machine we can consider as a tool. It is an instrument. And whenever you want to use a tool, right, you can consider the tool as a black box. You don't have to bother about how the tool has been developed. Don't bother about inside the tool, what are the different parts are there, screw, nut, bolts, the wire, batteries, so many things. You don't have to bother anything. What you want to consider most, you have to think about what is the input that can be given to the machine, and then what machine will produce against this input. So from a user perspective, a machine as a black box, it takes an input and produce an output. So our support vector machine does the same way. It takes an input and produce an output. Now let's see what is the output. As I already told, this SVM is used for prediction or classification. So it will give an output as a prediction whether today there will be rain. Answer will be yes or no. So output will be yes or no. A person, whether his gender is male or female, so answer will be male or female. Whether this fruits is sweet or not, answer will be yes or no, like that one. It is not that only yes or no, or male and female, or true and false. It can be any prediction value that is applicable. So two output, not necessarily the only. I gave example for two outputs only, but more than two outputs, so multi-output is also possible. For example, if you asks your machine to decide what character it is, A, B, C, D, the machine, it can decide it properly, tell that which is the correct character it is. So this way, multi-output is also possible from the machine. Now, so output is clear. Machine is bit clear. Now let us see what is the input to the machine. Now, input to the machine actually a vector. So vector is an input to the machine, and based on this vector, the machine will give prediction. That is a classification of the vector. That is an output. Now let us clear our idea about vector. So you know, possibly the simplest vector is a point in a 2D Euclidean space. Now, how such a vector can be defined? It can be defined either a two values. If it is in a two-dimensional space, it will be defined by three values. If it is in a three-dimensional space, if it is in n-dimensional space, then it will be decided by n values. So a vector is like this. Now, this vector is applicable, the concept of vector is applicable not only to the points in a space, whether it is 2D, 3D, 4-dimension or n-dimension, but it is applicable to any other real world where we can think some data in that way. I'm telling you one example. Suppose we were to consider the student's data. So how we can define a student's data? A student's data can be defined with a number of attributes. What are the attributes? Name, roll number, date of birth, address, mobile number, marks obtained in 5 subjects. Now, as you see, there are different values with which a student object can be defined. Now, each attributes is called one dimension. If a student is defined only name and roll number, so only two-dimensional object it is. If it is defined name, roll number, mobile address, 3-dimension. If name, roll number, mobile number, and then address, then 4-dimension, and so on. So the dimension decides how complex an object it is. Now this way, it is not that student, for example, a tree, you can define with a number of attributes, maybe height, what is the texture of fruits, flowers, the leaves, size of the leaves, picture of the leaves, and so many ways. Similarly, a fruit also can be considered as a vector. What are the dimensions of a fruit vector? The fruit vector's dimension may be size, may be texture, may be shape, may be color, may be taste, may be smell, and so many things are there. So in our real life, every object is characterized with number of features. That is also called attributes. So a vector is a mathematical way of representing an object in terms of their features. That is attributes. So a vector can be one-dimensional, it can be two-dimensional, it can be n-dimension. N can be any large value. Essentially, a vector in our machine learning techniques that is applicable in our real-world problem, they are high-dimensional vector. Now here I can give an example so that you can understand how the vector come into the picture of machine learning concept. Say suppose weather prediction. you want to apply machine learning technique to solve this problem. Now you decide what should be your vector. Your vector is today's, about today or one, maybe, okay, today's or maybe tomorrow's weather data. That data can be obtained from the satellites. That data includes what is the temperature, what is the wind flow, what is the humidity, whether there is a moisture or not, and so many things are there. So these are the attributes or features. And your data related to weather will be comprising with all those values. Now, if this is the input you give to machine, then machine will decide whether there will be a rainfall or what will be the weather. So it will predict. Now, this prediction you can have if you give, say, last 7 days data to your machine, and machine can take all those data and then produce an output. Maybe in coming 7 days, what will be the weather? Not only in 7 days, you can give the 30 days past data, maybe last 10 years past data. Now here you see, if you consider last 10 years past data that needs to be given to the machine, then your vector is too complex because it has so many data. So this indicates that a vector, by name, it is a very simple word, but actually implication is very complex. Whatever it is here. So vector is like this. And to our support vector machine, the vector is an input to the machine, and output is the prediction or classification of the data. That data belongs to this class. So these two keywords is sufficient. And now let's come to what we mean support. Now our objective is now inside or to going to the machine. That means building a machine. How we can build a machine. A machine can be built using some data. This type of data, it is called the training data. What it does mean? You can consider, say, last 30 years data, and then you just give your machine that this is my 30 years data, and you learn about the weather from this data. Now here you learn from this data, that means training data. So the machine, how it can learn given a training data to the machine? Here is an algorithm is required. This algorithm is called learning algorithm. So learning algorithm is one technique with which machine can learn from the input data. That is the training data. If your training data is very large, machine will learn correctly. If your training data is small, machine will learn poorly, right? So there is called underestimation of the data, so far the machine is learned. Now, so machine has to learn, and there is an algorithm. It is called the machine learning algorithm, by which machine can learn and then machine can be ready. That means the black box is ready. So this is a very simple procedure, but only few things that you have to learn about how a machine can learn, and that is actually called the support, right? So there are certain vectors by which machine can learn it very accurately, and it will give the accurate result. So those three things are very important, and then we mainly will discuss about how machine can learn. That means what is the concept of support in this regard. Now this SVM concept, it is not a new concept that it is a modern concept. Like, it is of course a very old concept. It is old means around in the 1990, there is one Russian mathematician. It is called, he was Vladimir Vapnik. That time he was busy with statistical techniques to handle data, and he proposed the concept of this SVM, but for the different purpose of learning, it is called the statistical learning. So statistical learning is the one subfield of machine learning. So he was a mathematician working with the statistics. He proposed the concept, and then he gave the new name as support vector machine. So it is actually used for that time it was used only for classification, and the latter time we can extend this application to regression analysis as well as ranking purpose. So according to Vladimir Vapnik, the idea is to find one plane. The plane is called hyperplane. Now here in this figure, as you see, one picture is a very simple picture, and it is related to two-dimensional data only. Now in this picture, you see there are different type of objects are there. One objects are symbolized with plus symbol, another object is cross, another minus, another is division symbols. Now actually they are different type of objects or category of objects, right? For example, plus represents fruit, apple, cross represents mango, minus represents orange, and then division represents a guava. So these are different objects are there. Now again, how an object can be defined, as I already see, all objects can be defined by set of feature values. And in this case, all objects are with only two-dimensional values. So only two features are there. And their point represents the position of each object. And this way we can see all objects which are very similar to each other, they are in one region, another object in another region, and so on. Now, so different objects, if you can see them, they can be grouped into a different region. Now fine, this is fine. Now what we can do is that how we can differentiate one object from other. So that differentiation we can do by drawing a line. So line is a separator. This separator says that you belongs to Pakistan, you belongs to India. You belongs to Bhutan, you belongs to Nepal. It is like this. So this is the boundary. Now in the theory of support vector machine, this boundary is very important because they can decide, that means the boundaries can decide an unknown object should be belongs to which region. And this is actually the classification problem. Now this support vector machine works this way actually, right? It will decide the boundaries. Boundaries mean it is a separator between two regions, each region representing object of one class. Now this support vector machine, I have already mentioned at the very beginning that it is old but it is gold. Now why? What makes it is superior down the time that so many other advanced techniques have been evolved, but still support vector machine, which was invented in the year 1992, but still it is very popular. This is popular because there are many other techniques which support vector machine does also available, but majority of them suffers from dimensionality problem. What is the meaning of dimensionality problem? They work better for a low dimension data, then data with fewer features. But when the dimension increases, that means number of features increases, they usually perform poor. Whereas support vector machine does not have this issue. Whatever be the dimension, it may be 10, it may be 100, it may be even 1,000. No issue, it will work perfectly. Now it will work, what do you mean by that? It will work in the sense that accurate prediction. It will work in the sense that the dimension may be very large, but it will take not much time, right? And it works because even if the fewer data available to build a model, that means to learn the machine, it is also still work perfectly compared to other technique. So far the accuracy is concerned, so far the prediction time is concerned, so far the model building effort is required, support vector machine outperform all the other classification techniques those are available in the field of machine learning. This is the thing, but there are some points that I should say, because you learn, of course, training time. That means the time that is required to learn the model from the input data, that is the training data, bit high, right? It is high because it can take very large dimensional data. That is why it may take little bit higher time. But this is not an issue. This is because we have to build a model once only. So it is a one-time job, right? And then we can do it offline. So let it takes around 3 days to build the model. No issue. We can do it because one time we can invest this amount of time. Once the machine is ready, we can test it. So testing is a very fast with this support vector machine, which is very important because a certain weather data that given to you and you have to predict about the weather, then if it takes much time, then definitely this is not a good machine. But if it takes only small time, in a fraction of seconds, then definitely you can say that that's a very good, I can use it in my application. Another problem is that there are two problems in the machine learning so far model is concerned. One is called the underfitting and then overfitting. Underfitting, the concept it is if your data is not balanced, right? If it is not balanced and then only fewer classes data is available, other class data is not so much available, they are scarce. On the other hand, overfitting problem, it is the idea in the context of noise and many other erroneous data if it is available. So your machine may learn wrongly. Now here it has been observed that both fitting and overfitting problem, so far the support vector machine building is concerned, not so much headacheful. It is simple. They actually, right, there is very less overfitting as well as less underfitting problem. Now you can understand that the support vector machine, why it is popular. So let's learn the support vector machine. Now in order to learn the support vector machine, I want to first teach you the concept, which is a key concept in SVM. It is called the maximum margin hyperplane concept. Once we learn about the maximum margin hyperplane, then we will see how such a maximum margin hyperplane can be obtained for a certain type of data, which is called the linearly separable data. And there are other type of data which is called linearly not separable data. So this way there are two, right, different type of machine, linear SVM and non-linear SVM come into the picture. Now, so let us consider about maximum margin hyperplane. So maximum, minimum, all those things is very common word. I don't want to discuss about it. What do you mean by maximum? Margin, what it does mean? Now suppose a river separates two regions on the earth. Now that separation will be called the margin. If the river is too much wide, then I can say that my separation boundary is very much, right, wide margin boundary. Wide margin boundary means so people from one region will not be able to migrate to other region and vice versa. So margin is actually how much width of the boundary it is. Now let's come to the hyperplane. Hyperplane concept, it is like this. Now what is the plane? Now forget about the plane. Say in a 2D region, right? How you can divide the two regions in a 2D space? What is required? You require one line. That line can be straight line or that line can be zigzag curvy line. So in a 2D space, there is a separator which is in the form of a straight line or nonlinear line. So this is fine about 2D. Now let's come to the 3D space. You can imagine what do you mean by 3D space, right? It is just like one bird is flying. Now, so it is a 3D space. A sphere is actually a 3D object. Now, in a 3D space, then there is again, you can separate the spaces into many regions. If you do this, then what is your separator? What is the form of separator? The form of separator definitely not a straight line. Straight line is enough for 2D space. But in case of 3D, we need a different concept. It is called the plane. Again, this plane may be smooth plane, and this plane may be a zigzag, what is called a mountain-like plane. So it is in a 3D space. So plane. Now, so line, then a plane. Now let us extend this concept to beyond 3D, 4D, n-dimensional data. So n-dimensional data, if it is there, then such a space is called hyperspace. An n-dimensional space is called hyperspace. And a region or a separator which can separates the space into two parts or more than two parts, then they are called hyperplane. So hyperplane is the simplest. So for 2D space is concerned, which is a line. Hyperplane is a plane simply if it is in a 3D. Otherwise, for more higher dimension, it is called hyperplane. So hyperplane is a separator in a hyperspace. It is n-dimensional space. Now, as you can recall, I just want to tell one more thing. Any object in a 2D space can be represented. It is actually a point. Any object in a 3D space can be represented. It is actually what? It is actually again another point. So the difference between the point in 2D and 3D, only the values. So only two values, three values. Now likewise, if it is in a 4th dimension, then any object on that space will be represented by a point, but this point will be defined in terms of 4 values. Likewise, in case of n-dimensional hyperspace, there is an object which can be represented by a point, but this point is decided by n number of values. And what type of values? They are integer or real numbers or character or string. What sort of values? Value can be anything. It can be a string, it can be a character, even it can be an image, it can be a real number, can be an integer, which is in the simplest type of data. But the support vector machine, which we shall discuss, that a point is represented by a n-dimensional data, and the value of each dimension is a real numbers. I told you that, okay, it is a simplistic things, but once you are mature about SVM, then you will be fit this technique even to any type of data. That means it is a mixed, or it is a, we can say, hybrid type of data also. So this is another discussion is required. But anyway, I just want to say that the data can be defined with any type of values, but here we will decide about only numerical values. And that numerical values also maybe integer or real numbers, whatever. So this is the concept, right? Now, let's come to the discussion about maximum margin hyperplane. So far, our classification task is concerned. So let us proceed about in this direction. By the time you have little bit idea about what is the idea about hyperplane. Now, I will elaborate this concept using a simple example so that you can understand. Now, suppose you have given n number of points. They are actually n records. I can say the data obtained from the n students. So this is T1, T2, Tn. So n number of records, students data. And this is your training data. So your training data is a collection of n records. Now these records, this data set D can be stored in the form of a two-dimensional table. In this two-dimensional table, How many rows? N number of rows. And for each rows, there is actually one record, one student's data. Now, how many number of columns are there? Anybody can guess how many number of columns should be there? The number of columns should be decided by how each student's record is defined. That means how many attributes that we have considered. If it is 2 attributes, then 2 columns. If it is a 3 attributes, 3 columns. If it is the m number of attributes, then m number of columns are there. So your training data will be very simple. It looks like a matrix of data of size m cross n, where n records and each record is defined using m number of attributes. So it is an m cross n matrix data, you can say. This is your training data. Now, what is the concept that we want to learn? Given this training data, that means the table data, how a machine can be built. Now, in a simpler size, let us consider only 2 attributes. So 2 columns and n number of data is given there. Now, in addition to these 2 data or information, there is one more information is there. One information is that how many different groups with which your data can be divided. That means, say, you want to classify all the students' data into EX group, A group, B group, O group, C group, like this one. Now, what it does mean? O means outstanding, EX means excellent, A means very good, B means good, C means average, D means poor, this kind of. Now, so there are suppose 1,000 students' data that is given to you. Their marks obtained in different exams. There are other activities, so many data is available to you, and you have to classify the data belongs to outstanding category or excellent category or like this. So this is called the level. More precisely, it is called the class level. So as I already said, this number of class level at the lowest case, it can be 2. That means they can be divided into 2 different classes, or it can be multi-class data. Multi-class data means more than 2 classes. EX, O, A, B, C is a multi-class data. Anyway, so in addition to the information about each records that is there in training data, which are defined with number of attributes, in this example A1 and A2, there are one more specification is required, what kind of class the data belongs to. That means that given the training data and you have been told that this data belong to this class. So we'll consider for a simple case, the plus and minus are the 2 levels. That means all data will be categorized into 2 different classes, plus class and minus class. Now, having this information, the idea is how we can divide them. Now, before going to that discussion, I just want to tell about it. There are 2 types of learning technique. One is called the supervised and another is unsupervised. So supervised learning here, if you can tell that this is one record and this record belong to this class. So this way, all record that is given to you, at the same time, you have been told that, okay, this record belong to this class. So each records are classified into some classes. And this is called the learning with specific, what is called the level specification. It is also sometimes called learning with teacher. What is the meaning of the learning with teacher? Whenever you teach a subject, right? Teacher tell the question and also at the same time teacher tell the answer. So this way students can learn and it is called the supervised learning. Opposite to the supervised learning, it is called the unsupervised learning, where this for each record there is no class or no level is specified. It is just one type of teacher, you know, who can know only the problems but cannot solve any questions for the student. So he only tell the problems and students ask the students to solve the problems. I don't know about the answer. Okay, you find the answer and you check that if all of your answer is correct, then your answer is correct. It is like this. So this kind of training, it is called the unsupervised. Unsupervised learning, sometimes it is called the learning without teacher, because you are learning from the net. internet. You are learning from the course website, and there is actually no teacher. You are learning of yourself alone. So this concept is unsupervised learning. But support vector machine, the machine which can learn, it learn based on supervised data. Supervised data means the record, and each records are characterized with levels of each. So support vector machine actually is a supervised learning technique. It is there. Now let's come to the concept of this data. Now here in this figure, somehow with this machine, my pointer is not working, right? So that I will not be able to show the pen and marker here. Anyway, I'm sorry, I don't know. So there are some problem. Anyway, so without pen and marking is a bit difficult. But anyway, let's see. In this figure, what you can understand, there are two different type of objects. One objects are symbolized as plus, and another objects are symbolized as minus. And then vertical line axis, and then horizontal axis. Horizontal axis is A1 and vertical axis is A2. They represent the scaling of the data. That means A1 attributes and what are the different values of the attributes. So it is actually A1 data in this direction x-axis, A2 data in the direction y-axis. So A1, A2 represent two axes, x-axis, y-axis like. Okay. Now here, for example, the cost and the comfort of a car. So A1 is the cost and A2 is the comfort. So along x-axis, the cost that can vary from 1 lakh to 1 crore, and then comfort can be vary from low, medium, high to excellent. This kind of values, it is like this. So this way, the dimension it is there. Now, whatever it is there, now here you can see the two different type of cars. Right? One is the low cost and then another is that expensive car. Now, so I want to just simply categorize that, okay, given a cost and comfort, whether it is low cost or expensive car, it is like this. So the two levels. Now, so what is the idea? You can learn this technique knowing the known data. So there, as you see, there are many plus symbols, they are known data. The many minus symbols represent unknown data. So these are known data. Now, given these known data, what exactly our requirement is that? Our requirement is that given an unknown data means one specific car is given to you and you have to classify whether it is a economic data or a expensive car, economic car or expensive car. It is like this. So you have to test an unknown data. Now, in order to test it, what you can do is, we can test these things by means of a boundary line. Now, boundary lines, as you see, here so many straight lines have been drawn. And you can see each lines can perfectly divided the regions into two regions where the two regions belongs to two specific type of data. So there are so many lines which we have drawn here. For example, as you see, 6 lines are drawn in between. Now, do you think that only these 6 lines are possible? Or there are many more lines are possible? The answer is, in fact, there are infinite number of lines are possible. All lines are correct. They can divide the regions into two particular regions. So all lines are correct. Now the question is there, then out of also infinite lines, which lines we should consider so that this line can be used to divide whether a data belong to this class or another class. A unknown data, for example, here, if it is come here, then this data belongs to which class, whether this class or this class. Now, if you consider this line, then this line says that this point, which actually my cursor is moving, it is actually belong to the minus region. But with respect to this line, right, it says that it is plus region and so on. Now here the problem is that although with reference to these data, infinite number of lines are possible, but all lines are not as such accurate or give the result so far the prediction of an unknown data is concerned. Now here is the problem. Then we don't know which unknown data it is, but only we have to find the baseline which we can consider to classify the region into two parts. Now, which line that we can think about it. Now, actually the idea is that that line we should consider which has the maximum margin. Now, this way the concept of maximum margin come into the picture. I can tell you one example so that we can think what is the concept of maximum margins are there. Now, here in this figure, look at little bit carefully. Now, two boundary lines which we have considered, one line is H1 which is red color and another line which is drawn as a green color, let it be H2. Now, out of these two lines, H1 and H2, which one is better line? So far, the prediction of an unknown data is concerned. Now, both lines are accurate so far the known data is concerned. That means those are the given, in terms of given data, both lines are correct. But for unknown data, we can't say which line will work better. But now let's see. Say suppose red boundaries, red lines, which is bit called wider. Why it is called wider? It is called wider because from this line, the nearest point towards the left and the nearest points towards the right, how much they are width. So the gap between the 2 points which are closest to this boundary, so far the red line is concerned, it is actually M1. And in contrast to this, the green line, it is called M2, for example. So if you see M1 and M2, M1 is much higher margin than M2. M2 is lower margin. The gap is lower. And then for red, the gap is higher. Now, this actually is a deciding factor. So whether a boundary with low margin is preferable or a boundary with higher margin is preferable. Now, if I don't say much thing, you will go for that boundaries which has the higher margin. Why you should go for that? This is because if the margin is higher, your unknown data will be predicted with more risk. On the other hand, if the margin is small, then you have to predict with higher risk. So your prediction will be good with reference to the boundary with higher margin than the boundary with lower margin. So the accurate prediction will be possible if we can decide one boundary which is having higher margin. Now come to this figure again. There are so many boundaries, and for each boundary you can calculate margins, and then out of these 6 boundaries you can decide that boundary which has the highest margin. Then problem is become very simple. Are kya baat hai? We can do it and we can draw lines and then we can decide the boundary margin and then we can pick up. It's a very simple solving problem, but it is not simple. This is because there are infinite number of such boundaries are possible. And then out of these infinite such boundaries, we have to find the maximum margin boundary. That is maximum margin hyperplane. Now this problem essentially, it is not solvable in real time. Why is it not solvable? Because we have to find the baseline out of infinite possibilities, and which is not possible in linear time or in polynomial time. So it is not solvable in real time. So it is a difficult problem. It is a hard problem, it is called. Okay, so it is a hard problem, and therefore we need some machine learning to solve it. So here, actually, your machine means in terms of known data, those are training data, you have to decide the boundaries, and your boundaries is actually the form of the machine. This is your machine actually. So in this figure, for example, H1 is my machine. H2 is not my machine. Although it works, but it does not work so accurately, then the machine corresponding to the H1 margin is concerned. So in this actually support vector machine, inside the machine, nothing but equation of a hyperplane. If it is a 2D region, then H1 is the equation of a line. So your machine, if you look through this box, and then machine look like the equation of a line. What is the equation of a line? Equation of a line is ax plus by plus c equals to 0. So the machine form of the machine is ax plus by plus c equals to 0. So if you go into deep, then you can see your machine is nothing but parts are A, B, C. So machine is composed of 3 parameters, A, B, and C. These are called ML parameters or SBM parameters. Now, given some set of training data, your task is to learn what is the right value of A, right value of B, right value of C. I repeat, your task is to learn the values of A, B, C. So there is an algorithm by which a machine can learn the parameters A, B, C. Now it's fine, very simple. It is okay, but it is simple and it is applicable to two-dimensional data. What about the three-dimensional data? Is the same ax plus by plus c equals to 0? I say no, it is not, because in two-dimensional data, a straight line is a hyperplane, maximum margin hyperplane. But in case of three-dimensional, it is a plane in 3D space. Now tell me how the equation of a plane can be represented. If the equation of a line is in the form of ax plus by plus c equals to 0, then the equation of a plane can be in the same way if it is a smooth plane, right? If it is not a simple plane, then the equation of it is ax plus by plus cz plus d equals to 0. So in 2D space, unknown parameters or machine parameters are ABC. In case of 3D, it is A, B, C, D. X plus by plus cz plus d. So 4 unknown parameters. Now let us extend into the 5 dimension. Then ax plus by plus cz plus dw plus e equals to 0. So A, B, C, D, E are the unknown parameters. So 5 unknown parameters. So as the dimension increases, so number of unknown parameters by which machine needs to be learned from the input data increases. So in general, in case of n-dimensional space, the equation of a plane is represented as a W1 x1 plus W2 x2 plus W3 x3 plus dot 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 plus W1 x1 plus W0 equals to 0. Now, as you see, in case of n-dimensional region or hyperspace, the equation of a boundary, that is actually the hyperplane, is very similar to its simplest form in 2D region, just like straight line. Now this is fine. It is the line, or it is the simple plane, or it is a simple hyperplane. But what about nonlinear concept? The nonlinear concept, there, the idea it is that how the equation of a nonlinear object can be represented in a 2D space, for example. Now say circle. How a circle can be? Circle is a nonlinear shape, right? How the equation of a circle can be represented? You can represent the equation of circle in a simple circle, x square plus y square equals to r square. What is the equation of a hyperbola? So we can write y square equals to ax plus b, and like this. Now here you can understand that here in case of simple boundary, there is a linear form, but in case of non-linear boundary, like circle, ellipse, hyperbola, parabola, the boundary is not linear form. They are in a, they are not in a simple form rather. So in general, the equation of a nonlinear line in 2D region can be given as a x to the power n plus b x to the power n minus 1 plus c x to the power n minus 2 plus dot dot plus d equals to 0, where the value of n can be 1 or maybe greater than any value of 1 depending on how much non-linearities are there. What I want to say is that let us only think about simple form, straight line, or it is in a 2D space or 3D space or n-dimensional space. We can represent using only few number of parameters. In 2D space, w1x1 plus w2x2 plus w0 equals to 0. In 3D space, w1x1 plus w2x2 plus w3x3 plus w0 equals to 0. So this is the way by which any boundaries in any n-dimensional space can be represented as wixi summation I equals to 1 to n plus w0 equals to 0. So this is the simple form of the machine which usually they appear. So actually our objective is to learn this kind of machine. Learn this kind of machine means learning the model parameters. That means learning the values of w1, w2, w3, wn plus w0. It is like this. So n plus 1 parameters have to be learned. If it is in a 2D space, 3 parameters. If in a 3D space, 4 parameters, and so on. So learning is a very simple procedure, right? And this kind of learning actually is the key concept of so far the support vector machine learning is concerned. That is why sometimes the support vector machine is called maximum margin hyperplane machine. Now, I will first start the discussion with linear SVM. That means how we can learn the machine which takes the linear form, and then in the next session we can go for the nonlinear discussion. So now this linear SVM, as I already said, that we have to go for finding the maximum margin hyperplane. That is why linear SVM sometimes it is called the maximum margin classifier, because finding this boundary is enough job that to learn the machine actually. Now we will see exactly the techniques or machine learning algorithms by which machine can learn a model. Machine learn a model means the equation of a plane, or rather we can say hyperplane, right? And what is the input? As I already say, input is the n number of records, and each records are defined with m attributes. And for simplicity of discussion, assume that all the data are classifiable into two classes. Let one is plus class and one is minus class. So plus 1, minus 1 also you can represent. So they are actually the representation of a class name. It is nothing with the value. So plus means 1 class, minus means 1 class. Or 0 means 1 class, 1 means 1 class. Or m means 1 class, f means 1 class. It is like this. So just a symbol. Plus means 1 class, minus means another class. So the data that will be given to you in the form of xi, where xi is a vector form. The vector form means it consists of n-dimensional data. M-dimensional data as you saw in this equation. So that means m number of attributes are there to define each vector. And then one column is there which represents the class level. So your data will be available in the form of a m cross n, right? If n number of records, that is unknown data, that is the training data that is given to you, input data, and it is defined with m number of attributes. But it is actually not m cross n, rather we can say m plus 1 cross n. Why I say so? Because the last column 1 there, they represent the class level. So this is also included there. So it is actually m plus 1 cross n dimensional data that is given to you. And then I'll just start the discussion with a simple 2D concept first, then we'll go for the n-dimensional data, which I have already mentioned that in case of a 2D plane, the equation of a margin or boundary rather will be represented ax plus by plus c equals to 0, which also we can represent the same way as w0, w1 x1 plus w2 x2. So it is actually x1, x2, they are the different dimension values. And w1, w2, w0, these are model parameters. Similarly, ax plus by plus c representation is same as the first representation w2. So two representations are actually same, but mathematically they represent in a different form actually in terms of xy, here in terms of x1, x2, in terms of ABC, here in terms of W0, W1 and W2. But the two different representation represent the same thing. That is what I want to say. Now here one point that I want to say about it. So suppose you have given a line and then one point is given to you. How you can decide that this point is in the left side of the line or is the right side of the line? I repeat the problem, right? You have given a line and the 2 points are given, right? 1 point is the left side of the line, another point is the right side of the line. Now, how you can decide that this point P1 is left side of the line, but not the right side, and vice versa, the another point P2, it is in the right side of the line, but not the left side. How you can decide it, right? Mathematically, how you can say so? So, as you know, with reference to origin, if the value of the lines, that means if you represent the value of x1 and x2 into the line, right? So as I said, x and y, they are the values representing a point. So if you put the values of x and y in the equation ax plus by plus c, given that a, b, c are known, then you will be able to find one signature line. So it's a value actually. So the value will be either positive or negative. And if it is 0, what it does mean? 0 means that this point lies on the line. If the value is positive, what it does mean? It is away from the origin. That means with reference to line, the point is that side which is opposite side to that of the origin point belongs. On the other hand, if it is negative, then what is the meaning? Negative means the point is the same side with reference to the line in the origin also. So origin and point are the same side of the line. If it is negative and if it is positive, then we can say the point is opposite to the place where the origin is belongs. So it is opposite side of the origin actually you can say. So this way we can distinguish whether a point is this region or that region. Only the measurement of sign it is there, right? So either greater than or less than. And equals 0 is very unlikely case, but equals 0 means that the point is lying on the line. Anyways, okay, if it is lying on the line, you can understand, you cannot tell that whether you belong to India or Pakistan, we cannot tell, right? You are belong to both countries. It is like that. But this is not desirable. So that can be resolved in different ways, of course. But anyway, we will assume that either greater than 0 or less than 0. So greater than 0 means opposite side of the origin, and then less than 0 means it is the same side of the origin. So a point will therefore, a line therefore will be useful to decide the two regions. And then any unknown point, if you give it with reference to this line, we will be able to decide in which side the point belongs to. So it is the plus side or minus side. So if it belongs to the plus side, then we can say this data belongs to the plus class. If it belongs to the negative side, then we can say that it belongs to the negative class. It is like this. The same idea can be extendable to any dimension. So here, for example, the data which belong to the m dimension, right? So it is m dimensional hyperspace. The equation of a hyperplane takes the form w1 x1 plus w2 x2 plus dot 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 plus wm xm plus w0 equals to 0. Here plus w0 is equals to the minus b value. That's okay. Now, so if you have given unknown point which is defined by m different values, and if you put the value into this form, equation 3, and then it will result a sign, positive value or negative value. And that positive value or negative value will help you to decide whether this point belong to this side or that side. This side means plus side or that side means negative side. It is like this. So this way, this hyperplane concept, it is useful to predict the data into two levels. I say two levels. I'll tell you the same idea how it can be applicable to the higher levels. Now here one mathematics that I can apply it, so that this kind of form W1 x1 plus W2 x2 plus dot 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 Wm xm equals to B can be represented in the very compact form. What is the compact form representation? It is called the W dot x. What is the W? W is a matrix. What is the x? X is another matrix. What is the dot? It is a dot product of two matrices. Now, for example, W is a one-dimensional matrix, is a row matrix, and consider X is another matrix, is a column matrix. Both are of m cross 1 and 1 cross m size. So W dot X, if you multiply, then definitely you will get the value, this kind of form, W1 x1 plus W2 x2 plus Wm xm, this equals to B. Now, so here, W dot X plus B equals to 0 is a very compact representation of a model, or it is actually the representation of a support vector machine. Now here, if I say so, how your support vector machine looks like, you say my support vector machine is, it looks like W dot X plus B equals to 0. Now how many unknown parameters are involved? One unknown parameters which is directly evident, it is B, and one more, it is W. But W is a matrix, it is a vector actually, right? So W has m component values or m values. So W dot X plus B equals to 0, which we have learned earlier, it is actually model representation, but in a compact way. So your support vector machine, which looks like W dot X plus B equals to 0. So this is your machine. Now in this machine, as you see, input will be X. That is actually a vector. And output will be the sign W dot X plus B, it will return a value. Now if it returns the positive value, then we can say that X belongs to positive class. If it returns a negative value, then it belongs to negative class. Now let's come to the discussion about how this W and B can be calculated. So there is a bit mathematical manipulation of the simplest concept that you can think about, which actually the Vladimir Bhatny gave it in year 1992. So the idea is that, say suppose two type of data, one is X plus and X minus. As I say, X plus means it belongs to one region, X minus means it belongs to another region. Now, if we give this data to your machine, so W dot X plus B, it will give a value, let it be K. And if K is greater than 0, then means it belongs to one side. On the other hand, if K is another value, say W dot X minus plus B, it gives K dash, and K dash is less than 0, then we can say that this X minus belong to another side. Now these two facts can be represented using a form that Y equals to plus or minus. I don't bother about the value, I only bother about the sign, whether it is a positive value or negative value. So if it gives a positive value, then I can say it is one side. If it gives negative value, then I can say it is another side. So here the concept of this actually represented in the form of these values are there. As you can see here, so this is the equation of your model, that is actually your machine, W dot X plus B equals to 0, and then these sides, the positive, and these sides are negative. So X plus data is this side, X minus data it is there. Now here little bit, okay, one tacit representation about that. With reference to this margin, we can say this is the one closest point in these sides, and this is the one closest point in these sides. So if we draw two parallel lines, which is parallel to this red, but passing to the closest line, both sides, then these two lines, parallel lines, are called boundary lines. Boundary with reference to this, what is called the margin. So this is actually the boundaries, and this and the difference between the two parallel lines, or the distance between the two parallel lines, are essentially called the margin actually. Now let's see, if it is a W dot X plus B equals to 0, this is the your machine, or it is a boundary, then what is this side? This side can be represented using this value, W dot X plus B equals to 1. What is this equation? This equation can be represented w dot x plus b equals to -1. Now here you see +1 and -1. How it can be +1 and -1, that I can tell you this way. So here, say w, so for example here, that's okay, here, any line which is passing through the closest point x plus, which is in the that side, it's k. Now if I divide both sides by this equation, so w by k dot x plus by k plus b by k equals to 1. And that is actually same equation as w dot x plus b equals to 1. Similarly, if we in this form, then w dot x plus b equals to k dash, it's actually right -1. So w dot x plus b equals to 1 or w dot x plus b equals to -1, they essentially represents the two parallel lines, parallel with respect to this, and these two lines are equidistant from this plane. So this way, the equation of the two boundaries can be obtained. Now, if we can obtain the equation of the two boundaries, we have done many things actually. What are the many things? We can easily calculate what is the margin. So margin is essentially the distance, or we can say perpendicular distance between the two planes. So this plane and this plane. Okay, and this boundary can be calculated very easily using one formula. It is like this form. So it is the perpendicular distance between the two boundaries. So 2 by root over w1 square plus w2 square plus wm square. Now there is a few things that you have learned about, that if we can know the w1, w2, wm, the model parameters, then we will be able to know how much margin this boundary is having. And it is the formula equation 10 which can give you, it is there. So this way, the two margins that we can obtain, and then out of the two margins, which are the best margin can be decided. So the problem here it is that out of the two so many margins, how we can select the best margin. Actually, we have to search for that, because it is an infinite number of margins are possible, and out of the infinite margins, we have to search for the best margin. Then it is actually a searching problem. So it is actually search for the best values of W and B. So this problem usually, Vlamid is represented as finding the objective mu WB. That means we have to find the W and B so that the margin is maximum. So it is actually an optimization problem. The optimization problem is in the form of a searching problem. Now this formula actually Vladimir cleverly manipulated with some mathematics. I just tell this mathematics before jumping to the way how this problem can be solved and what is the search technique that we can follow. This is essentially the learning technique actually it is used. Now here you just note down. So w dot xi plus b greater than equals to 1. What it does mean? It means that xi belong to one side, positive side. On the other hand, w dot xi plus b less than equals to -1. What it does mean? It means that xi is a vector which belongs to the negative side. So that is why we can say xi is one side having yi, that means its class level is 1. And this xi having the class level yi is -1. Now this equation 13 and 14 in fact can be represented in only one equation. How it can be done? You just look about it. So yi multiplied by w dot xi plus b greater than equals to 1. It is actually always greater than equals to 1, because if yi is positive, then it is greater than equals to 1. If yi is negative and this side is negative, so it is greater than equals to 1. So this equation 15 can take care of any value, any vector xi, and then which level yi, and it is actually the same for any value. So all vectors satisfy this equation 15 actually. Now out of these all vectors, some vectors which are lying on the boundaries, the vectors which are lying on the boundaries. Now as in this figure, as you can see here, few vectors lying on the boundary. So for example this one, but here this one, like 2. Now the vectors which are lying on the boundaries, they are very much crucial vector or crucial data point. because they decide the margin width or gap of the margin. And these vectors, those are lying on the boundaries, they are called support vector. Now here question is that how many support vector usually we have for a given set of data by which we can learn a model. So suppose 1000 training data set, means in your training data 1000 vector is given. Out of these 1000 training vectors, how much belongs to the support vector category? Support vector means they are lying on the boundary. 50%, then 50% belong to support vector, and other 50% they are other sides but not on the line. So it is not 50%, 50%. Then, so 90% support vector, 10% non-support vector, or vice versa. 10% support vector, 90% non-support vector, which one? Actually, many data, okay, experiment with many data, it is observed that only few data are lying on the boundaries. Only few, maybe say 5% or even less than. So out of 1000, maybe 50 are lying on the boundaries, maybe both sides on boundaries, but remaining 995, they are not on boundaries. So number of support vectors, actually, it is very small. But this is one clue, because this information is very crucial information which we can tell and to defend many other things about support vector machine. What I want to say is that there are some point in your input data set which lying on the boundary. So far your to be estimated hyperplane, and then they are support vector. And your equation of the support vector takes this form. Now in this form, W and B are the unknown model parameter that needs to be calculated. So this actually should be calculated. That means W and B value should be found out in such a way that the mu, that means mu means this value should be greater. And this value actually in the simplest form 2 by square root of W1 square plus W2 square plus W3 square plus dot dot Wn square. So this is essentially a searching problem. We have to search for the optimal values of W and B for which this maximum margin gap is okay. We can find a boundary with maximum margin plane. Now this is a maximization problem, but we can convert it into a minimization problem by changing the numerator into denominator and denominator into numerator. So this is called the duality problem. Okay, which is reciprocal. If it is maximum, then reciprocal of this is the minimum problem, and like this. So this way we can turn into the problem in a minimization, writing mu WB into mu dash WB, where the mu dash takes this form W by 2, where W is root over this form. This form is root over W1 square plus W2 square plus dot dot plus Wm square. Now this problem is pretty simple. You have to find the value of W in such a way that this is minimum. Now how you can find? Given your unknown data xi, the n number of data, and for each xi, yi level is available. So you have to satisfy this constant yi into w dot xi plus b greater than equals to 1 for n points are there. So n inequations we can say. So you have to find the value of w and b in such a way that these 17 inequations are satisfied. Equation 17 actually represented n number of inequalities. So we have to satisfy this, right, n number of inequalities so that we can find the WB. Now this is a mathematical problem. That means you have given xi and yi values and this inequation to be satisfied, and thereafter the W and B value will be calculated, and this value can be calculated in such a that this become minimum value. So this is the problem. Actually it is a simple mathematical problem, but this problem can be solved using a very nice method. This method is called Lagrangian multiplier method. Okay, I just take 10 minutes more, and then so within 10 minutes I will complete the coverage of Lagrangian multiplier method, and this will complete a part of the linear SVM. So I will give an example how this Lagrangian multiplier method can be applied to solve this problem. That means problem means we have to find the value of WB such that yi w dot xi plus b greater than equals to 1 for n such values. So this problem can be solved using Lagrangian multiplier method. Now Lagrangian multiplier method actually applicable for two kind of problem. One is equality constant, another is inequality constant. In case of equality constant, the constants are with equal sign. For example, this is a equality constant. But in case of inequality constant, constant are of this side. Both are minimization problem. So minimize so that the n number of unknown value to be calculated given this is the condition. Now, so definitely our problem is belong to this second category, inequality constant optimization problem. But in order to understand the inequality constant optimization problem, it is better to learn first equality constant optimization problem. So let us first start only 2 minutes is equal to learn the each technique, and then only we'll be able to solve the support vector machine. It is a matter of time only. Now I'm discussing about Lagrangian multiplier method. Now in contrast to this Lagrangian okay, fine. So let's see what is the Lagrangian multiplier method is. Lagrangian multiplier methods consist of fewer steps. The first step is called the define Lagrangian. What is the Lagrangian? Usually it is represented L. So L equals to. What is the L equals? It is actually fx. Fx is what? It is the objective function plus whatever the constant that is given in your expression, each constant multiplied by a Lagrangian factor, or it is called the Lagrangian multiplier. This is called the lambda I. So if there are p number of constants are given, so p number of multipliers, lambda 1, lambda 2, dot, lambda p. And for each constant, lambda 1 into constant 1, lambda 2 into constant 2, plus dot, plus lambda p into constant p. So this will give you the first form, it is called the Lagrangian. It is usually denoted as L. In this equation 18, I represented within x lambda. Actually, it is L. Now, once this L is given to you, then you will be able to find the first order derivatives with respect to each unknown. Now, let's see what are the different unknown that is here. Now, here, as I see that fx, the objective function is to find the xi unknown x1. It is actually in this form. So x1, x2, dot, xd. So d number of unknown and p number of constants are there. So what we can do is that with respect to each unknown, if we take the first order derivatives of this Lagrangian and then we can make it equals to 0, then it will give a equation. Similarly, lambda I, the Lagrangian multiplier is also unknown because we have considered the one multiplier. So if we take the first order derivatives of this with respect to each lambda I, so it will give you the p number of equations. So here, first order derivatives of equation 18 with respect to each xi and with respect to each lambda I will give us d number of equations plus p number of equations. So d plus p number of equations. Now, how many total unknowns here in this d number of unknowns and lambda I, so p number of, so total d plus p number of unknowns. Now you can see total d plus p number of unknowns, and then we have d plus p number of equations. That means this system of equation is therefore consistent, and if we can solve this system of equation, we will be able to calculate optimum values of x1, x2, dot, xt, and then the unknown values of lambda I, which used as a parameter also. So we will be able to solve this problem, right? And then all the unknowns will be available, and then we can solve that, we can obtain the optimum value. So this is the idea of the Lagrangian multiplier. And this is one simple example that you can think about it. So this is suppose objective function fxy, where only two unknown x and y, which takes this form x plus 2y. So this is a very simple form. And only one constant that is given to you, x square plus y square minus 4 equals to 0. As the equal sign is 0, so it is equality constant optimization problem. Now we can represent Lagrangian L is equals to x plus 2i plus lambda, because only one equation, x square plus y square minus 4. Now del L by del x, this gives one equation. Del L by del y gives another equation, and only one lambda, so del L by del lambda it gives. Now if we solve these three equations, then we will be able to calculate the unknown value x, y, and lambda. And then based on which we will be able to find the optimum value, which is the optimum value, that is from this equation solving we can find. And then this actually objective function can be solved. It is the same idea here in our problem. So we can have this n number of input training data, and then that n number of equations you are having, and here m number of unknowns that needs to be calculated, and then we can apply the Lagrangian multiplier. But in this case, you see constants are not equal. So now let's come to the what is the method which we can apply to the another type of problem. It is called the inequality constant optimization problem. This problem very similar to the previous one, but with a little bit difference. Difference I'm telling you. So like the previous one, first Lagrangian, this is objective function plus for each constant lambda into this one. So if the p number of constant, this actually extended is there. Now here in case of equality constant, we find only one constant with respect to all unknown, the first order derivatives. But here, in case of inequality constant optimization problem, Lagrangian technique is to find what is called the KKT constant, Karus-Kuhn-Tucker constant. Actually, this constant, if we apply over this Lagrangian, it will give you a system of equations. And if we solve this system of equation, all the unknown here as well as all these unknown will be solved. This is the idea. Now let's see what is the KKT constant. This is the KKT constant, very similar to the previous one. First order derivatives of L with respect to all unknown. Then lambda 1 greater than 0. Now this is very important constant. They say that lambda I value should be always positive. No negative value is allowed. Then this is the constant that is given to your expression hix less than 0. And lambda I hix equals to 0. This is the another constant that you have to think about it. So this is the one constant which is very similar to the equality constant. This is the added value, one constant that lambda I should be greater than 0. This is the equation, it is a constant again. And this is another constant that is fixed, it lambda I into hi should be 0. Now, these are the different constant. If we apply to this Lagrangian L, then it will give you so many system of equations. And definitely if they are sufficient to solve the unknown, number of unknown parameters, then definitely they are solvable. So here is an example. So suppose this is the objective function in terms of x and y. So x and y are unknown, and this is the one. And the inequality constant is x plus y less than equals to 2. And another constant is y greater than x. I can represent both the things in the form of xi plus less than equals to 2 and x minus y greater than minus 1, this way. So this way I can obtain the Lagrangian. This is the objective plus lambda 1, x plus y minus 2, this one, and plus lambda x minus y. So this if we can have, then we can apply over this L, del L by del x, all the unknown, plus lambda I greater than 0 and so many constant, then it will give you so many equations. So as you see, these are the so many equations can be obtained. So this system of equations, if we can solve using some numerical methods, then all the unknown value, namely x, y, lambda and lambda 2 will be solved. Here 4 unknown and so many equations including, and then they are solvable using some numerical method. And that solution will give you the optimum value or desirable value solving the support vector machine. So this way, for the support vector machine, we shall be able to obtain the unknown model parameter, that is actually the knowing the model. Now let's come down to the our support vector machine equation is there. In this case, our Lagrangian will be W by 2. But for the sake of simplicity, I am using the square. Absolutely, this is not a problem. Lagrangian actually effectively will be the same as earlier. So I took the square for the simplicity in calculation, that's all. And yi w dot x plus bi greater than equals to, but so far the Lagrangian condition is concerned less than equals to 0. So I took out a minus sign and this one. So this is my Lagrangian. And in this Lagrangian, unknown parameter w1, w2 dot wm and so many lambda I that is applicable, so that these are the unknown parameters. So if I apply inequality constant optimization technique for Lagrangian multiplier over this Lagrangian, we will be able to calculate the unknown parameters. So here, these are unknown, del L W, del L B, it will give you this formula. This is a very important formula, you just note down. W is equals to I equals to 1 to n, lambda I, yi dot xi. Xi is a vector, y is the class level, lambda is actually an unknown constant to be null. So W is in this form. Now del L by del B equals to 0, it gives you another expression lambda I into y equals to 0. And this is lambda I greater than 0. And lambda I, this is also another constant. Yi, this is also another constant. Now, this is the system of equations. And all this system of equation can be solved using any numerical method. And then we will be able to know the unknown values that is there, W1, WB, and then all lambda i's. And thereby we will be able to solve the problem. Now, in this case, as you see, if we know the W and B, and then for an unknown vector xi, we will be able to get the positive or negative sign. And that actually the classification technique is on. So your classifier actually is an estimation of del x value, which is nothing but W dot x plus B. So it will return a value with sign, positive or negative. And if it is positive, then x can be one side. If it is negative, then x can be another side. So del x, sign of this del x is actually the deciding factor. Now I can see how this can be represented in a simple form, because W no, W is summation of lambda I y dot x and then x plus b. So this is very simple. Now here you can note down xi dot x. What is xi? Xi is a vector, right? There is actually input vector, which is in the training data sheet. And what is the x? X is actually your unknown vector. So xi dot x, it is a dot product. So this is a scalar quantity, lambda is a scalar quantity like 2, 3, 4 value, y is plus 1 or minus 1 value, xi dot x is another dot product, it will also give you the dot, or what is called the scalar value, plus b is also a scalar quantity. So altogether it will return a value, positive or negative. And this value will be used to test what is the unknown vector in which direction. So this way, the hyperplane, this is the equation of a hyperplane. The hyperplane will test an unknown vector x, in which level, in which class it belongs. So positive class or negative class. And to know these things, all the unknown value that needs to be calculated. B should be calculated, W should be calculated, and WB, all those should be calculated using Lagrangian multiplier method. Now I should stop it here, and then I have just concluded the discussion about linear SVM, but this linear SVM in terms of, linear SVM in terms of linearly separable data, right? And how they can be utilized. But it is again solving the binary class problem. That means the data that is available to belong to two class. Now, what about if it is a multi-class data, it is there. Okay, I think I should give around 20 minutes break, right? So we shall back after 20 minutes and we'll start from here, how the same concept which we have learned for binary class SVM is applicable to multi-class SVM. And then I'll go to the nonlinear SVM quickly. And learning nonlinear SVM will not take much time. Only the concept I just will clear it so that you will be able to actually nonlinear SVM, in fact, linear SVM in disguise. Okay, so we'll discuss about the nonlinear SVM, right? Before that, we'll discuss about how the simple linear SVM that we have learned can be used to solve multi-class classification problem. Okay, so after break, we shall be back. Now, if you have any question, you can do one thing. We can keep all the question ready so that at the end of my session in the second part, right, I can take up all the questions and discuss. Let us have a little bit break, right? And then exactly we shall start around, okay, again, 12 o'clock. Yes, one question from Deepak. So definitely one real example, actually it is in the slide, but to shortage my time, I just skipped it, but I'll give one example, okay? Yeah, definitely I'll give one real example so that you can understand. So in the next section, I will decide about it. Okay.
Good afternoon, sir.
Good afternoon, Nidhi. Thank you. What a fun day, okay?
We welcome you back, sir, and all the participants. Please be active. Sir is back again, and we start the session soon.
Okay, now I'm ready. Can you start now? Nidhi, can you start now?
Yes, sir.
Okay, fine. So, so let me share my screen again.
Yes, sir.
Yeah, just okay. Let me know whether you can see my screen.
Yes, sir. We can see.
Okay, good. Now, one question I got. Okay, some of you have asked me to elaborate the concept that I have discussed about with a small example so that you can understand. Yeah, so I just okay. This is my objective now. I just give an example so that you can follow the concept. See, my problem is here, right? So we want to find the value of W and B. Given that for the n number of training data, right, we have to find the proper value of W and B, right? Now let us consider one example. So we'll consider few data, n maybe 8 or 10, and with in terms of those 10 data, how the unknown value W and B can be calculated. I can tell you one example so that you can understand. So suppose this is your data set, right? As you can see, this is your data. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. 8 data are there, right? 8 data points is given. Out of the 8 data point, as you can see, 4 belong to positive class. So this data in positive, and this is also in positive, and this is in positive, and this is in positive. Rest of the negative class. So it is a 2-class problem, right? Now, so this is actually x1 and x2 for first data, x1 and x2 for the second data, and so on. Now, So using this data, what we can do is we will be able to obtain this constant that is required for our Lagrangian multiplier. So this is the Lagrangian multiplier. We consider that this is a two-dimensional data. So W is W1 square plus W2 square by 2. This is the Lagrangian, and this is actually, you can see I equals to 1 to n. So in this case, n is 8. And yi, one class is plus 1, another is minus 1 into W, that is the unknown value that we have to in terms of, and dot xi. Xi has the two parameters because xi is a vector here, right? So xi has the two values, right? So these two values are here, like these two values are like, okay, so it is a x1 and it is a x2. So if you put this into that expression here, into that expression, right, you will be able to, that expression here, you will be able to find this Lagrangian. So this Lagrangian can be obtained. So it's very simple. L equals to root over, right? It is not root over will be because we have taken square. So it is W1 square plus W2 square by 2 minus I equals to 1 to 8, yi will be plus 1 or minus 1 depending on the data belong to positive or negative class, W into xi plus b. Actually, this is a simple form which can be obtained after this Lagrangian multiplier method using the Karuskal-Tucker constant. So this way we can get it. Now here, as you can see in this example, so w dot x, actually w will be lambda I, yi, xi. So this is the w. Now how I can get it? So this can be obtained by using this first order derivatives. First order derivatives of with respect to day. So this is actually this one. So we can have it from here only. And del L by del B, another constant that also can be obtained. So here we can see all these constants can be solved. And if we can solve, then all unknown parameter lambda and all the unknown parameter W can be calculated. Now, as in this example, right, if you solve this using linear equation, then we'll be able to find the values of lambda 1, lambda 2, it is like this. So for this data, right, so lambda 1 can be calculated as this one and lambda 2 also can be calculated this one for this, right? Actually, pictorially, this data, it is like this. So these are the 4 points with a positive class and 4 points, negative class, out of which one is on this one and another negative point is this one. So in this example, as we see, we have calculated solving the KKT constant, we got this value, and these two values says that positive value, it is actually lambda 1, and all other data point for which it is 0, they are not support vector. So in this case, these two are the support vector. Okay, so these two are the support vector. So these two are the support vector. These two are the support vector because they lie on the boundary here. So this is the first one and this is the second one, lie on the boundary, right? And then you see after solving this KKT constant, W1 is obtained as this one and WT is obtained as this one. And now let's see how the B can be obtained. So for calculation of B, some simple calculation is required, which is actually in this form. As you know, so this is actually in the KKT constant only if you can apply. So this can help you to solve these values, which can be obtained like, so W1 is lambda I, yi, xi, and WT is this one because this actually W is equals to summation of lambda I, yi over 2 component value. So this way W1 is calculated and W2 is calculated, which are these values. And then B can be calculated using this value. B1 is, because W dot x plus B equals to 1. So this way the B1 it is like this. And B2 it is like this. And in both cases B1 and B2 are the same. So taking the any one value as B, or you can take the average value. So whatever it is, B will be calculated as 7.93. So what I want to say is that for this example, our objective is to find this one. To find this, we apply the Lagrangian multiplier method. And then
KKT constant. Solving the KKT constant, we got the value of W1, W2 and B. So here, this actually the equation of our model, or this is the support vector machine in this case. So this is the support vector machine. Now with respect to the support vector machine, this x1 and x2 for any unknown point, if you check it, always they can give you negative for this kind of point, and all this kind of point it will give positive value. Now let us consider an unknown value. On unknown value, say it is an unknown value. X is 0.5, 0.5. So here in the picture, unknown value maybe it is 0.5 and or it is 0.5, it is like this. So unknown value it is there. So suppose this is the unknown value it is given. Now let's see how it can be calculated. So it can calculate it that this del x is negative value. So del x is negative value. This means that it is towards the origin side. So okay, so a little bit calculation or picture drawing is not there. So it looks that okay this side, and so it is actually negative value. So this point rather will be look like this. Okay, so this side like negative side, because with respect to this line, this point is towards the origin, and if it gives positive value, then with respect to this line, it gives positive value in this side. So this is the one example that can help you how the unknown parameters can be solved using Lagrangian multiplier method, and then the margin or maximum margin hyperplane. This is the maximum margin hyperplane in this case can be calculated. Okay, so this is actually solving the SVM, and this is actually the support vector machine in our case in this particular example. Okay, so this is the problem that we have solved it, and as you have noted it that this problem has been solved for two-dimensional data only. That means 2D points. But how this can be solved for multi-dimensional point? This is the next question that I want to give the answer. Now, such same linear SVM that we have learned, we can think about solving for multi-class data, but there are two strategies available. The two strategies, they are called OVO in short form, and it is actually an abbreviation of one versus one strategy. Another is OVA, one versus all strategies. These are the two very standard strategy, popular strategy, out of which OVA is more popular than OVO. Now let us first learn about what is the OVO strategy and OVA strategy. Our objective is that how the concept that we have learned can be applied to solve the multi-class data. That means data is not only two class plus and minus, maybe plus, minus, star, division, 4 class or more than 4 class. Now let's see how this can be done. So let us first discuss about one versus one strategy, OVO strategy. Idea again pretty simple. What is the idea? Say suppose you have the n different classes. Then you take for each class as 2 pair. For example, there are 3 classes. So plus, minus and cross. So what you can do, you can consider only 2 type of training data which are belong to plus and minus class. And for this, you will be able to build one model, one machine, say it is SVM 1 by H1 machine. Then take plus and cross. Another machine you can build, and then take minus and cross. Then another machine. So if there are 3 class data, then we can consider 3C2 number of machines. So you have to repeat the same linear SVM for 3C2 times. So 3C2 is actually 3. Now in general, if there are n number of classes, for example 4, so 4C2. If there are 5 classes, so 5C2. So 120 or like this, we will be able to build so many what is called the machines. So definitely, if the number of classes is increases, this strategy is in a very costly affairs then. But anyway, let us see what is the idea about it. So we can have NC2 number of SVMs or NC2 number of maximum margin hyperplane. Now each hyperplane will be useful for classifying 2 data type. For example, here 3 type of data. So one model this one, another model this one, another model this one. So this model can divide the region belong to 2, plus and minus. This can divide plus and star, and this can divide star and minus. So you can understand. So okay, 3. Now, so for this 3 class data, we can have it, and for more data, another boundary will come. Actually, this depends on how many data points are there. So now here, for each points, for an unknown data, for example, your unknown data is belong to this class. So this is the unknown data, and this is here only. Now, for this data, if with respect to this class, it give positive value, and for this classifier, this data also give a positive value, and for this classifier, this also give a positive value. This means that this data belong to this class. Now, so if we can find, the idea it is like this, right? So if there are n number of classifiers, if you can apply NC2 pairs, and then so many classifier, if we build it, then we will be able to test for your unknown data for that. Say suppose this X is the unknown data that needs to be tested, and with respect to I, the J classifier give one sign. So with respect to I, for each others, it will give sign. If we find one I for which all del Jx, for all others, give the same sign, then we can say that the unknown data X is belong to the I class. So this way, we have to test it, and then we can check it that how we can classify the data belongs to one class only. Now this problem, this classifier is very simple, of course. Only the problem is that we have to build a large number of classifier models. If it is a 2, only 1. If it is 3, then 3 models. If it is 4, then 4C2. So 4C2 means 12 models. And as the number increases, so you can understand the number of models that needs to be built is increased. So each pairwise, so you have to take, and one more requirement in this strategy is that because we are considering only subset of data belongs to only 2 class, so definitely the size of the input training data set should be as large as possible. Then only it can give good result. We can avoid under fitting problem. So this is a problem of this technique. Otherwise, it is a very simple one. Now let's see another technique, which is called one versus all strategy. It is the OVA strategy. OVA strategy, conceptually, it is very simple. What is the idea? Say suppose you have k different class levels. Then we can think about, say, one data belong to one class, say it is C1, and all other data belong to another class, say star class. So what you can do, we can build a model C1 versus star class. That means it is again linear SVM can be, because it is a 2 class problem, we convert into 2 class problem, and then we can build a model and let it be H1. Likewise, we can take C2 data, that means data belong to C2 class, and all other data belong to other, say, star class. So C2 versus star. So another model can be built, it is say H2. And this way, k number of models can be built. Now here, in case of OVO strategy, case C2, if the k is very large value, so number of models that needs to be built is very high number of values. But here only k number of models to be built. So this way, this strategy is more, right, more efficient. We can say efficient in the sense that more fast actually to test a data, because only we have to build k number of classifiers. Now, once the k classifiers are built, then for an unknown data, we can test it. For example, so this is the unknown data. So let the unknown data be X, and with respect to, say, C1 classifier, so J is 1, we take the del X value. Now this will give you positive or negative value. Now likewise, J can be changes from 1 to 2. So for with respect to CT, it can be calculated. Then del X value will be obtained for the same unknown data. So this way, with reference to K classifier, so del X can be calculated and K number of del X value will be obtained. Now out of which can give the maximum values of del X, actually it will be that classifier. So if the jth classifier give the maximum value, then we can say that AX is belong to the class CJ. So this is the idea about OVA strategy. So certainly OVA strategy is better than the OVO strategy because it is faster than OVO strategy. Another thing is the data, okay, even the small number data, OVA strategy works well, but OVO strategy needs a very large set of training data to solve it. So this is the idea about the multi-class classification problem using two strategy, OVO and OVA strategy. Now let's come to another problem, which the data that given to you to classify, they are not linearly separable. Rather, they are non-linearly separable. Now, our understanding needs to be clear what you mean about linearly separable data and non-linearly separable data. Now, here I am giving you one example. So here, as you can see, in a 2D plot, no issue, we can explain it. In this 2D plot, these are the data by which we can draw a boundary between the two regions, which can be in a linear boundary. If a linear boundary can be drawn to separate two regions, then the data, this kind of data is called linearly separable. But here, as you see, no line can be drawn. Rather, we can draw one curvy line, it is like this, so non-linear line. No straight line we can draw. Now then we can say these are the data which is given here in this example, they are not linearly separable. They are called linearly non-separable data. Also linearly not separable data also we can say, or not separable, okay, linearly, right one. So this kind of, for this kind of data, therefore, if we apply the previous concept, definitely it will give the result with very poor accuracy. It will very bad result. So this problem is there, and then the machine that we can think about, it is called the nonlinear machine needs to be considered. Now I'll discuss, there are many techniques for dealing with this one, but I'll consider one technique that is purely using the same concept of linear SVM but solving nonlinear SVM. That is a very interesting problem. So let's come to this one. I'll skip this one because the first technique I don't want to discuss. I'll discuss only using the basic concept of linear SVM, but we can apply to the nonlinear SVM concept. Now here idea it is like this. Idea is, so this is the example of a linear SVM, right? Because here this is the linear SVM. Now here data it is given to you. Then the hyperplane, as we can see, it is nonlinear. This is also another nonlinear. Now this hyperplane, what sort of equation that you can, if this takes the form ax plus by plus c equals to 0, then it will take the equation of the form ax square plus by plus c equals to 0. And this equation takes the form ax square plus by square plus c equals to 0. Now here, from the data as they are plottable on 2D plot, and having this data, we will be able to decide what sort of nonlinearity and what is the equation. This is the equation of a hyperplane, this is the equation of an ellipse. So we can just convert into this form and then we can get it. But in general, if it is an n-dimensional data, we cannot visualize them, and therefore we will not be able to understand about what kind of hyperplane it is, and then accordingly the equation. So this concept visually, if it is suitable for lower dimensional data, but for higher dimensional data, we cannot. And therefore, we need to find a totally different concept it is there. As you can see, if this is the equation of a linear form, and this is the equation of a nonlinear form. But this nonlinearity can be of infinite time, because whether degree 2 or degree 3 or degree any, and then whether there is a monomial of this term, because the peculiarity of the nonlinearity, and so this equation 31, actually the infinite form it is possible. So this kind of form, even if it is not visually available in this form, but mathematically if we want to solve it, then the infinite number of type of equations that you can think to represent the hyperplane, they're again not possible actually. So there are so many problems that we cannot solve using our traditional concept of the thinking and hyperplane and then solving it using Lagrangian multiplier method and then get it, because you have to try out with all possible values are there. Now, in order to avoid this, there is one problem, one solution. This is a very simple solution. I will explain you how the solution actually it is there. Solution is that transforming the data from a lower region to higher region. What it does mean? So if your data, for example, 2D, you transform the data into higher dimension, say 3D or 4D. It is the idea it is. Say suppose you can see a surface area, right? It is 2D. Now you can see the surface area from the space. So it will then again 3D view can be obtained, right? So then in 2D space, which appears to be a very smooth plane, but if 3D point, then whatever the ups and round and the peak and trough, everything can be visible there. So the idea it is like this. So idea again, transform the data from lower dimension to a higher dimension, so that the data which is in lower dimension not linearly separable, they become linearly separable in higher dimension. Now let us take an example so that you can understand. Say suppose this is the one equation of a hyperplane which takes this form, and then definitely this is the square term and this is the monomial, this is the binomial term that you can see two terms are available. They are against the nonlinearity. So if up to this part is nonlinear, linear, but considering this one, they are nonlinear terms. So this indicates that this is the equation of a hyperplane which takes a nonlinear form. Now we can represent this into a linear form, and then means that then hyperplane become a linear form. And if it is if we can convert it, then our previous concept can be applied to solve this problem. So now let us see how this can be converted into linear form. We just simply have few transformation function. They are called phi 1, phi 2, phi 3, phi 4, phi 6. As here is 6 terms, so 6 transformation function. What is the transformation function? Z1 is x1, it is simple transformation. Z2, again another simple, these are simple. But here, this is the one transform function you can see, it is just like y equal to x1 square. Another transformation function, y is x1 into x2. Another it is like y is x1 into x3. Now, if we represent this form in terms of this z value, where z is in higher dimension, then this will be converted into a hyperplane, but not in 3 dimension, but in higher dimension, that is the 6 vector, or it is called the 6D space. So this form will look like this one, right? So it is right. So this is the actually linear form, as you see. That means you see the previous expression x in 3 dimension, x1 coordinate, x2 coordinate, x3 coordinate, which has the nonlinear form. If we transform into higher dimension, it becomes linear form. So this kind of transformation if we can do, and for this example, the transformation that is required, these are the 6 different function is required. Now, the problem here is that this, technique is very simple. This technique is very simple. And for an example here, for example, say this is the 2D data. For this 2D data, this is the nonlinear form and this is the linear form. So this nonlinear form we can express because it is the equation of an ellipse look like. So it is the nonlinear form. And we can convert it into the Z form, which take this form. So Z form is actually in the, right? Z is equals to, this is actually Z1 and this is Z2. Okay. So this form look like this one. So this is the transformed value. Now here you can see this equation Z1 plus Z2 is a linear equation which take this form, right? So this is actually linear. So we transform the data from this to this one. Here for this particular problem, 2-dimensional in the original space and then transfer also 2-dimensional in the place. But we can, right, separate the data. All plus data is this sides and all negative data is there for this side in transform. And this is actually linear SVM that we can plot. The linear SVM is this one, which can classify the data in this one. So this is an example where the transform data can be converted and then linear SVM can be applied. but it has many problems actually. This problem, although very simple, but the problem is that so how the mapping can be obtained. For here, in this case, we got the mapping this form. So there is a phi 1x and phi 2x. Provided that we know it, but we see from the data, we will not be able to see what sort of form it is there. So this is available only if we learn the model. But before learning the model, how we can do it? So as we are not able to know the model structure in this form, so we will not be able to find the mapping function which can take this form, and then therefore this kind of mapping can be obtained. So this mapping itself is a very difficult job, and it is mathematically next to impossible to solve it. Although the conceptually it is very simple. Another problem is that dimensionality. Whatever the transformation function that we can think for lower dimensional data or only fewer dimension, it can thinkable. But as the number of dimension increases, number of transform function also increase, because the hyperplane takes the very complex form. And therefore, dimensionality, if it is large, then this is really not possible, and compression is also very expensive. So the problem that we will not be able to solve with the very simple idea that we have discussed, that is the transformation method, it is not solvable. But there is a good point is, the good point is that the linear SVM which we have learned, the same thing we can apply to solve the non-linearly solvable data, for which we have to little bit manage the linear SVM, and then we have to apply one tricks. This is called the kernel trick. So now I am going to discuss about non-linear SVM building concept, and before that I will discuss two solutions. One is called the dual formulation, and then kernel trick. And note that in case of our simple linear SVM, we formulated this problem as a Lagrangian optimization solving problem. Now here, same problem solving, it is different little bit from the previous one. It is called the dual formulation. And another thing is called kernel tricks. I will discuss the kernel tricks in details when we will come to that portion. So first let us consider about what is the dual formulation of the problem. Now you note down, in our problem, originally it was, it is actually minimized. So assuming that our equation of the hyperplane is linear, and then equation takes the form w1 square plus w2 square plus dot 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 plus wn square root, and take the square mean it is the square. So it is the sum of square terms. And this is your objective function, for which we have to calculate the different w1, w2, w2 values, so that this value is minimum. Now our constant is also readily given. If you have given n number of data, x1 to x, x2, x3 dot dot xn, then our constant will be like this one, which is our actually problem, that is actually our SVM solving problem. So the learning technique is to solve this problem so that all w values and then lambda i's values can be calculated, and then we can. So the Lagrangian polynomial we have already used for that. Now for that purpose, as you can see, we have discussed about, for that purpose we have discussed about the Lagrangian value. And this Lagrangian value I am just intentionally expressing LP, because it is called the primal form. Now this is actually the Lagrangian which we have learned, and this is also called primal form, or primal form of the Lagrangian, right? And here lambda I are the Lagrangian multiplier, and then this summation extend over n number of points. Now, so this is the Lagrangian, and we also show you how this Lagrangian can be solved using KKT constant. So that if we can have the KKT constant applied to it, so that all unknown here, here and here also can be solved. So this is a numerical problem. Now we are going to define a little bit different way of solving the same Lagrangian. If it is primal, then let's see what is the dual form of the Lagrangian. So it is nothing but a mathematical calculation. Now, from the dual primal form, as you know, if we take del L by del W, mean with reference to unknown, if we take the first order derivatives, and that is equals to 0, it will give one form, which you have already learned earlier. And with respect to B also, it gives another form. So these are the two equations we can obtain it from these two constants. Now, let us apply all these equations into the primal form and little bit go for simplification here. So this is the, if it is the LP, then after submitting these values of W and this expression into this form here, okay, and then little bit go simplification, you will be able to find that it will come to this form after simplification. So here you see there is no W, there is no B. And further one bit more simplification it will give here. Now this kind of form that we obtain after simplification and applying W and B into this equation is called dual form of Lagrangian. So it is actually called L. So essentially this LD and this LP are same, but only the thing is that the value which are here and the value which are here are different. Now, what is the important point that you can note? Here, the LD, dual form Lagrangian, only takes the value of lambda i's. There is no W, no B. So, Lagrangian become more simplified because only on one type of parameters, unknown parameters to be solved. And as you see the one example that I show you, that if we know the Lagrangian, then we can know which are support vector. Now, Lagrangian for which non-zero values for this parameter, they are support vector because they leads to be the point which are lying on the boundary. And those are 0, they are basically away from the boundary. So only non-zero values of the lambda values, if we collect those data, then only few points, because if lambda is 0, then this term will 0. So only for non-zero values of lambda, this term exists, right? And then this form is actually only in terms of here, because I told you how many support vectors it is there, maybe 5%, maybe 10 to 15 support vector out of 1000. So this expression is not a very big one, and solving this expression even manually also not so difficult task. Anyway, what I want to say, this is actually simplification of Lagrangian from the primal form to a dual form, and it takes this form. Okay, so this is the idea that I want to tell, and this is the dual formulation of the problem. Now, this dual formulation have its own inherent advantage. What is the inherent advantage that you take it? So, by solving this Lagrangian, according to Lagrangian multiplier, lambda I or lambda j, all these values are available. Now, here you see lambda is a constant value. This is also a constant value. So, lambda I, lambda dot, it is simple multiplication. Y plus 1 or minus 1. It is also simple multiplication. But xi and xj, they are not simple multiplication. This is because xi is n-dimensional data and xj is also another n-dimensional data. Actually, it is a vector. Then xj another vector. So here is the product. So what is the idea? Idea is that xi dot xj is a dot product. You know vector product. There are two types of product, dot and cross product. So it is actually a dot product of two vectors. Now dot product of vector finding is very simple, right? So this LD can become a simple product only, and except few summation term, because for some value there will be non-zero, there will be summation. So summation and product only the two operation. So it is not the costly operation. Now here the idea is that we will be able to solve the problem very simple way if we can transform the primal form into dual form, and then solving this dual form to decide the test vector. Our test actually, testing, this is actually the testing formula, the lambda dx, which is the same as earlier, w dot x plus b, because we replace w here and b. So this also very pretty simple. B can be calculated easily using the expression that if you know all the other lambda values, b can be calculated using that w dot x plus b equals to 1. So b equals to 1 minus w dot x. So if w is known in terms of this, then b can be calculated easily, which I have given an example here. So this is actually the tester, del dot x, and this tester can be obtained using replacing unknown. This is actually unknown value, and these are the test data, right? Input data value, and taking some few dot product, and then this value will return you either a positive value or negative value. So del dot x actually a value, actually it store a value, and if it is positive, then we can say that it belongs to positive class. If it is negative, then we can say belong to negative class. The same concept which we have learned earlier, here also we can apply it. Then what exactly the concept that the data which is linearly solvable using primal form, if the data is linearly, and using dual form, we can solve similar kind of problem, but with less computational effort. That is what the idea. But we have not addressed so far the non-linearity problem. Now let us see how we can address the non-linearity problem and how the kernel trick is for there. Now here you can note down, we have given the idea about that non-linear to linear transformation for which some transformation is there. Now here kernel tricks help you to find what sort of transformation function that you can think so that data which are non-linearly separable become linearly separable. Actually kernel tricks nothing but finding the transformation actually idea. Now let's see how the kernel tricks can work for us. The idea again, I repeat from the previous discussion. If this is the data which is linearly not separable, and after phi transformation, we can transform the data into this part and this part in such a way that linearly separable is there. Now this phi is actually some magical function which will transform this data into this form and all positive data, right, into this form. So this magical function, which one is this magical function? So magic function is actually we don't know, but here the kernel tricks can help you to find the magical function. Now again I am repeating the previous example. So if the data which is defined in terms of 2-dimension data, and after it transforming into higher dimension, it becomes this one. So here this is the phi function. So the phi in the x dimension, it can be converted to z dimension, and this is the z transformation. So this is actually the nonlinear domain, and we can convert nonlinear domain into linear domain in this form. So the idea is pretty simple. So this actually, as you can see in the previous example, if this is the classifier for which we have to know lambda I, the Lagrangian multiplier unknown parameter that's to be calculated in x direction, in the z dimension, z domain, it is the same thing, but xi should be replaced by phi xy, that is the z transformation, and x should be replaced by phi, this is one. Now here what I want to say, I repeat again. So this is actually in a non-linear domain, and after transforming by means of phi function, we can convert into linear domain. So this is applicable non-linear, this is applicable with linear, but application okay followed by transformation function. Now again, using our duality concept, we know this is actually the minimization problem, and then we can solve it again using our Lagrangian multiplier as usual, because it will lead to some values same as the KKT constant, but here the KKT constant in terms of phi xi and phi xj. Now here again, this how this x to phi xi, xj to phi xj can be. So this is actually the classifier, and this is actually the learning technique. Learning technique using dual form, not that primal form. That's okay, right? But in case of dual form, even we know phi xi, phi xj. Now here exactly the kernel tricks help you to find what should be the proper phi xi that will help you to transform from x domain to z domain. So it is actually like this. So our data in x domain linearly non-separable, in z domain linearly separable, how the transformation can be done. Now I will tell you this transformation function, and by means of kernel tricks actually it can be obtained. But before going to that, let us interpret the representation, what it does mean x dot I. If x is a vector and y is a vector, what is the meaning of their dot product x dot I? If we can crack this one, then we will be able to crack the concept of kernel trick actually. Now see, x dot y, if you know a little bit vector algebra, then you know x dot y actually magnitude of x, magnitude of y cos theta. So here x is a vector and y is another vector and theta is the angle between them, right? And so this is the x vector and this is the y vector, right? So if we take the magnitude of this vector x and magnitude of this vector y, then x dot y is equivalently xy equals to cos theta. So this is the dot vector. Now here one thing you note. So if cos theta is equals to 1, then x dot y is equals to xy. Now cos theta equals to 1 means theta equals to 0. So theta equals to 0 means the two vectors, they are called similar. So if the two vectors are similar, then what we can say that x dot y is the highest value. On the other hand, if two vectors, one vector is this and another vector is this, so that angle is 90 degree, then cos theta is 0. And cos theta 0 means this x dot y is 0. Now x dot y is 0 means what? X dot y 0 means the magnitude is with the lowest value, because this cos theta vary from 0 to 1. Okay, if the angle is from 0 to 90 degree, otherwise all other angles are conformative. So this way, so this way we can check that how much similar the two vectors are. X and y, they are very similar if their cos theta is the highest value. If they are non-similar, they are very dissimilar, also called they are orthogonal, if their value cos theta is 0. Now often this x dot y is denoted as cosine similarity and used in many machine learning technique for the similarity estimation. So the two vectors given to you, two student data given to you, you can say that how the two student data are similar to each other. So what you can do, you can just calculate x dot y, the dot product of the two vectors. And this vector, if it is a 0.9, then we can say very similar. If you say 0.01, then we can say it is not so similar. They are mostly very dissimilar. So this gives us some magnitude so far the similarity measurement is concerned. And this magnitude or similarity measurement in machine learning is called cosine similarity measurement. Now this cosine similarity concept, actually we can apply this cosine similarity concept to these our kernel tricks, and we can solve our nonlinear SVM problem using this concept. Now let's see how this cosine similarity problem can be leading to a kernel trick concept. The idea is that if xi and xj are two vectors in original dimension, and then phi xi and phi xj are the two vectors in the higher dimension, and if xi dot xj denotes the similarity of the two vectors in the lower dimension, then phi xi, phi xj, they also represent the similarity of the two vectors. But this similarity in lower dimension, whereas this similarity in higher dimension. Now tell me whether the two similarity measurement is same or different. The two similarity xi dot xj in lower dimension and another similarity measurement phi xi dot phi xj in higher dimension. Actually, so far similarity is concerned, similarity will not change if the dimensionality of the vector changes. So essentially, this xi and xj and phi x and phi xj, they are very similar. They are very similar. They are same. That means that the xi dot xj and phi xi, phi xj can give us a clue that we can replace xi dot xj by phi xi, phi xj very comfortably because they are similar. But we can do it provided that phi can be obtained to us. Now, in this case, the phi, the magic function, actually called the kernel function. Now, here I will tell you how the kernel function can be obtained. But before going to that, let's see the one idea that we have already explored in case of the previous example, so that it is actually this is the example that I have given here in this example actually, exactly. So there is a hyperspace in 2 dimension, another is 3 dimension, which we obtain replacing this by Z transformation into this form. Okay, so this is the formula we can again, let us go here, how they can be right. So here, this is the transformation which we have already learned. Now we just want to elaborate that how xi dot xa and phi xi dot phi xa are very close to each other. Now here you see, this is the xi, xa vector, and in case of phi xi, this is actually z1, z2 and z3, it is actually replaced there. So phi xi function. Now let's go to little bit there. So phi xi dot phi xa, we have this vector and this vector. So this is a dot product. So this is the dot product vector. And little bit simplification give rise to ultimately what we can see, this phi xi phi xa is same as xi dot xa. What it does mean? If phi xi dot phi xa gives value say 10, so it is actually square root. So phi xi dot phi xa is a 10 square or square root. So they are magnitude wise, they are maybe square but proportional. So essentially these two things are same actually. Essentially phi xi and phi xa and xi xj are same, but magnitude may be scaling different. It is like this. You want to convert the currency from Indian rupees to dollar. So equivalently your wealth is same, but amount is different because the currency is different. It is like this. So phi xi, phi xj, it is in a dollar, it is in Indian rupees. That kind of concept is there. But what I want to say that they are same, they are equivalent. They will not lose any physical meaning anywhere. So xi dot xj and phi xi dot phi xj are the same. Now, after having this realization, what we can do is we can replace xi dot xa, which is same as phi xi dot phi xa, both can be replaced by one k function. Here this k actually called kernel function. That kernel function can, if you can find a kernel function so that this kernel function can give the same, this equivalent, this equality, this implication. Okay, so this kernel function actually is very important or pivotal thing that you can think about it. Okay, so this is a very important one expression that you can think about. Okay, now here the idea is that how this function can be obtained. How this function can be obtained. Now let us see how this function can be obtained for for your own data set. I'll tell you the idea for that. Now anyway, so suppose there exists a function, k function, where k xi xa gives you the same equivalent value that of xi dot xa, equivalent value of phi xi dot phi xa. And this function is kernel function. Now suppose we found a kernel function by some means and let it be the k function. Then what we can see, the del x we can replace by del x is actually, you can recall lambda yi xi dot xa. I can replace by this kernel value. So this becomes our classifier, right? And then that is actually learning. We have to maximize in terms of kernel value. And this is again dual form, and it can be solved using Lagrangian multiplier. All lambda values and unknown b value can be calculated after solving this one. So model parameters can be learned, but in terms of kernel value actually. So here the data needs to be little bit transformed from your data site into a kernel data. Now let's see how the data can be transformed and how the mathematical procedure that can be applicable. So here, as you can see, computationally it is very fast, even faster than using primal actually, and even faster than using dual also. if we replace by kernel 1. Because kernel will get the value of similarity measure. You don't have to go for dot product. And dot product is the costly affair, because if the vector of higher dimension, then lot of multiplication involved. But here you can do it. Now there are a lot of mathematical techniques have been evolved to help this computational expensive. And there is a two concept. It is called design matrix and gram matrix, which I will discuss shortly. After that, I will come to again kernel 1, and then we can decide how we can fit our data in terms of some kernel. So first, let us see, using these kernel tricks, how the SVM can be solved very efficiently. Here, the two ideas that I want to first discuss is a very simple idea. You just simply listen to me. First of all, you have given your training data set. That is your input data to build the model. And this training data set, let us denote it as X. So in your X data set, how many records are there? X1, X2, xn data are there. Now see, this xn actually, it is a vector, right? This is a vector. This vector means it can be expanded to represent x1, x2, xn. So if the n dimensions are there. So essentially, this is actually a matrix. Matrix of size n cross n, where this n is the number of attributes and it is the number of training data. So this is actually matrix in this form, right? And this is, we in our SVM, it is called the design matrix. So it is essentially your training data set. And this training data set can be represented using this form. And it's a very simple matrix form. And you see, the matrix representation is an ultimate representation in deep learning technique, where the artificial neural network or any other matrix, that is why MATLAB is coming there in the computation, so that you can apply MATLAB to solve or to develop this kind of problem or implementation. So it is all sort about the matrix operation, nothing else. So all data can be stored in the form of matrix. We go further and we'll see that it is all about matrix only. Now let's see. So this is your input data, training data set, and which you can store in the form of a matrix. So if it is 100 data, no issue. So only the number of rows will increase. That's all. Okay. So it is absolutely, we can store your input data in the form of a matrix. After that, we can obtain another matrix. It is called the gram matrix. Actually, it is called the kernel matrix, we can say. What is the concept here? This can be obtained from here, x dot. See, this is a matrix, and if we multiply this matrix by itself again, then it will give this kind of one. Now here you see this matrix actually n cross n. So it is actually, we can obtain x and then dot x. If we x cross x, rather we can say. So this is a cross product of two matrix. If we get, then it will give. So here you can see x1, x, and this diagonal, if you see, they are basically dot product with the same one. But if you go this side, it is x1 is multiplied with x2, x1 is multiplied x3, and so on, x1, x. On the other hand, this side of also if you give, then it is basically same. So out of the whole thing, only one diagonal part is sufficient for us. So this actually what it gives? It gives that similarity between any two data that is there in your input training data set. So it calculates all similarity estimations between any xi to any xj. And this is also one-time computation, and that also only half of the computation of n cross n, that is also enough, and we can store all similarity measures. And this similarity measure in terms of your raw data, that means your data in your original data set, right? Now we can replace this value if we know one k function by k matrix. So that can be again obtained the another form. So we can just simply from there we can write another matrix where for this value the k into, for this value we can write k into x, right, I and x j. right? So it is any entries are there for any aij. So this is actually right. So it is actually, if you know kernel, of course, then we will be able to obtain. If you know any kernel, then we will be able to obtain this same calculation not from your raw data but on the kernel value data. Now here you see, once it is available, then this actually the classification model that I told you, it is available to you so that you will be able to find the classifier quickly, but it is in terms of this one. And then machine can be learned in terms of k only, and then b all unknown parameter can be learned. So this is the idea actually. Now here the problem is that everything depends on finding this k function actually. Everything depends on finding this k function. So kernel function. And this is crucial. Now let's see how this problem can be solved so far your data is concerned. Your data related to banking transaction, your data related to weather prediction, your data related to simply handwritten character recognition, whatever it is there. For every sort of data, you should have this kernel function for right in your first as the requisite so that you can apply it. Now let's see how we can solve this problem, finding the kernel function. And this is the table, only few kernel functions which I have listed here. But there are very standard kernel functions. So usually our research scholars, they start with your given data and then check with each kernel one by one. So it is actually trial and error method. And which kernel method, it will give the best result, that actually is your clicking method. I repeat again. What is the idea? Idea is that in the field of machine learning, there are few standard kernel functions are there. Now I just listed few. One is here, as you see, linear kernel. Another is called polynomial kernel. Another it is called the Gaussian radial bias kernel. Another is Laplacian kernel. Another is sigmoid kernel. Another is Mahalanobis kernel. I have listed 6 pretty simple but very powerful kernel. Usually your data should be fired with any one kernel. That means either Laplacian or Gaussian or linear or polynomial, anyone. What is the consequence of that? Consequence of that, say suppose your data is fireable with Gaussian kernel, and Gaussian kernel K for two vector x and y can be computed using this formula. And in this computation, you will see there is few parameters c and sigma square. Sigma square actually called the variance of your data, and c it is called the mean of your data, right? So by knowing the mean and variance of your given data, you will be able to calculate kxy. So for any xy, you will be able to get the kxy calculation. Now come back here. So for any xi, xj, if it is Gaussian kernel, then this value can be obtained. So this become your gram matrix, contains the result. And this gram matrix therefore will be used in this equation to calculate the classifier. So del x can be obtained in terms of this one. Now here, as you can understand that, so kernel function, you have to take it. You tried with linear kernel, you got very poor result. So you can stop it. Then stop it. You find good result. Right? Very moderate result. Not acceptable. It is also poor result. It is also bad result. So then you can see it. It is like this. So you can test with your linear SVM, but replacing the xi.xj using this k method, and then test the result using your classification technique for unknown data, and then accuracy can be calculated, and then which kernel give you the best accuracy, that is your right fitted accuracy. And this is the idea. Now in order to apply a particular kernel, then definitely you need some value to be calculated. For example, here the lambda value can be calculated. There is a precise method using this Laplacian, how this lambda can be calculated. Lambda actually is the mean of the data that is available there. So the Laplacian means if you plot the data along this direction, and this is the data distribution, and this is the mean. So this is actually the lambda value that you can obtain. So actually plotting the data in a distribution, there are many graph methods available. You'll be able to calculate it. For each kernel, therefore, some parameters which is required, all those parameters can be obtained from the given data, and therefore the k value can be calculated. So all k value for any kernel can be obtained, and replacing that kernel, you will be able to get the problem solved. This is the idea about it. And there are different kernels, as I have already explained. And here you see, this is the polynomial kernel that is footable. If your data, it is not linearly separable, but non-linearly like this form. So this is the polynomial, and if you apply this polynomial kernel to is, and in the fitted region, it will be basically linear. And this is a sigmoid. Sigmoid is actually, it is like S, summation. The data is actually linearly non-separable. And then sigmoid kernel actually can give the data in this way. So this is actually the idea. So idea is that if the data in the original data space, and if you apply the sigmoid kernel, they can convert the data, giving their similarity measures equivalently same. And this is the Laplacian form, the x data and y. So x and y, the mean and can be calculated, so that you can convert x and y, and accordingly the Laplacian transformation can be obtained. This is the Gaussian RBF kernel, which we have given one example. If the data which is like this one and another is this one, and this is the one convex region that we can use for classification. After RBF, the data will be, right, it is like, so this is a similarity value in non-linear region. But this is actually transferable in terms of a k, and this k is from the RBF kernel. Okay, so this way the transformation that we can apply and we can solve it. So this is the idea that nonlinear SVM can be obtained. Now here you note down, nonlinear SVM is nothing but linear SVM, but only in the back of kernel. And kernel, as I said, to apply, you check that which kernel can help you to get the best result, and accordingly you get it. So only here is the only problem, that you have to repeat your machine building with different kernel and then test the result and then check that which kernel gives result. If you don't know, of course, what sort of kernel that is applicable, that is what. If you know that my data satisfy, for example, the polynomial kernel, because it is pattern like this, then straightaway apply and get the result. Or if you think that my data satisfy the sigmoid kernel, go for that. Or Laplacian kernel, or Gaussian RBF kernel, go for that. So if you know it, that's fine. Otherwise, if you don't know, check out with many other kernels and then take it. And this way you can solve it. So this way nonlinear SVM can be solved, and then you can get it. Anyway, other things are not so much important. What I want to say is that the SVM learning problem, that means how to get the optimum value of the model parameters, is more, right, better algorithm compared to many other traditional classification technique which are known in the market, like decision tree based, like Bayes classification technique, like neural network based classification technique, whatever it is there. So we can do it. And SVM is the best suitable to classify whether data is linearly separable or non-linearly separable. Because for the linearly separable, we can apply the linear SVM. For non-linearly separable data, we can apply non-linear SVM. But non-linear SVM, nothing but linear SVM. So non-linear SVM is the ultimate SVM, which can take care whether data is linearly or not linearly. You don't have to go for any test. You don't have to bother about it, that whether my data is linearly separable or not. Just go away straight, directly apply non-linear SVM. Essentially, non-linear is the same as linear, but only non-linear SVM is with kernel tricks. Linear SVM with it the dot product, absolute majority of the measure of the dot product only. Only the two difference between the things. So you can understand that how non-linear SVM, but from the linear SVM. Now, as I said, the data value that we have considered for each attributes, linear data is numerical. So all the calculation, so far this kernel is concerned, as you can see, all this kernel calculation is a mathematical calculation. And if it is a mathematical calculation, because it's a function, right? Some function. So function takes some values, returns some value. So this value usually the numerical value. But there is again problem is that whether kernel SVM can be applied to non-numerical data or not. Non-numerical data, namely categorical data. Categorical data mean category means whether female, male, or high, low, moderate. These are the categorical value. Or it is string, roll number, or address. All those things are there. Now, what I want to say is that SVM definitely better people have applied to classify the numerical data like integer or real numbers, but there have been an attempt by which the categorical data can also be applied to SVM. But truly speaking, transformation from categorical data to numerical form is under some lossy transformation, some loss will occur. I can tell you one example. Say suppose age. Age in a categorical form like young, child, then moderately young, old, very old. So these are categorical data. Now I can transform the categorical data into numerical data like, for example, child. I can say that if the age in between 1 to 15, then there is a child, and 15 to say 30, then I can say they are young, and 30 to 50, I can say moderately young, then 50 to 60, I can say old, and 60 above, I can say very old. Now here, what is the idea? If we see one data say old, then that old data can be replaced by 65. So this way, that data from the categorical domain to numerical domain can be converted. But again, whether old can be 61 also and then 70 also. So all of a sudden I took 65. It is apparently taking a middle value. But some people may tell that let's take 61, let's take 69 or 70. That also I can take it. So there is a doubt. But this doubt coming because lossy transformation may occur. You can just, okay, definitely 65 gives some accuracy, 61 will be same, 69, but they are not of the same accuracy, right? So accuracy may change. So that is why some problem is there. So truly speaking, that is why I'm telling that, okay, SVM, usually we don't apply for categorical data. For categorical data, Bayesian classifier is the best technique we can think. And next to Bayesian classifier, we can consider decision tree-based technique, which is very much good for categorical data classification. But for numerical data, SVM is the number one, right? And computational cost for the SVM is also very fast because building the model with only fewer computations. That is also very simple product of the values and summation of the values. So multiplication and summation. And that also only fewer data because, as I said, that summation and multiplication took place for only support vectors. And number of support vectors is very negligible compared to the whole training data set. 5%, 1%, 2%, or so. So the computation effectively only fewer computation. It is true for both building the model as well as for testing the data. Once the model is built, that means you have learned the model parameter, your w.x plus b equals to 0 is available, and then testing it for an unknown data x also very, very fast. So it is good, right? Both computationally building the model as well as testing, it is, it is good. So this way, this can give you better result. Okay, so this is actually at the end. I have another 10 minutes or so that I can come up with some questions from the participant and then discuss about it. If you have any doubt or any question, you can ask, feel free to ask any question, no issue. Okay, so one thing you can do, you can type your question in the chat box. So from the chat box, I can get the question. I can reply to each and everyone. And that, I think that is the best way. Otherwise, someone can moderate so that they can collect the question and then let me know the question, whatever it is there. Okay, I got few questions from you. One question it is like this. So one question that I received from Professor Gupta, SVM is used for clustering. No, SVM is not for clustering. Clustering is a different learning concept, different machine learning concept. SVM is used mainly for classification. So in machine learning, there are two techniques. So far the learning is concerned. One is supervised and unsupervised. Clustering is unsupervised. So basic idea of the clustering, it is like this. You have given n number of data as a training data, input data, and you have to group them. For example, in case of support vector machine, you have given n data and you told that this data belongs to class apple, this data belongs to class mango, this data belongs to class orange, like this one. But in case of unsupervised learning, you don't told that, okay, which data belong to which. So 100 data is given, and then from the data, you have to group them. So all the data which are belongs to class apple will be grouped together. All data which are belong to class mango will be grouped to another, right, mango group, another orange group, like this one. So from the group, then we can predict that, okay, this data belong to group, say, apple, this data belong to group mango, this data belong to group orange. It is like this. So although it can leads to the same, but the process is different. Process is different in the sense that in case of SVM, it will tell you directly your data belong to which class. But in case of clustering, it will cluster the data. From that cluster, you can interpret that, okay, this data belong to this group, which is different than the other group. Then you can name the group that, okay, this group is A, this group is M, this group is O, like this one. So this is actually the technique. So truly SVM is not applicable to clustering, because in case of clustering, there is no level is required. But here in case of SVM, leveling is must. Without leveling, SVM you cannot build. So SVM is not used for clustering. Now another question from Dilkeshwar Pandey, Dr. Pandey. So your question is, it is only for classification and regression. SVM actually is applicable for three purposes: regression, as well as classification and ranking. What is the idea of the ranking? Say suppose your data is multi-dimensional data. Now if it is a one-dimensional data, you can sort them in ascending order or descending order, like say marks obtained by the student and then rank the student. So highest marks will be rank 1, next highest will be rank 2, and so on. So ranking for one-dimensional data is very simple, but ranking for two-dimensional data, three-dimensional data, n-dimensional data, it is non-trivial task. So here the SVM also can be molded so far how the ranking can be done. This kind of problem needs a different discussion, different, again, another presentation required, and there is a concept called the trans SVM. So that application of SVM to rank the data, multi-dimensional data can be ranked from higher order to lower order in this order. So ordering the data, it is basically sorting multi-dimensional data, you can say. Sorting multi-dimensional data, but using SVM. It's a very interesting topic to learn. Another regression, you know, regression is actually prediction problem. So regression means if you know that this is the age and this is the mortality. This is the age, this is the mortality. Now can you predict that if this is the age and what is the mortality, or vice versa? So regression is actually in the form y equals to fx. So x is a dependent variable, independent variable, and y is the dependent variable. Now, so there again, simple linear regression or non-linear regression, because this function y equals to fx may be simple function, linear function, maybe non-linear function. So again, non-linear SVM can be applied if you want to predict in terms of non-linear regression model. So here the SVM can be applied there. So in this session, we have learned only classification tasks, but we didn't cover how the regression or how the ranking can be done. Yes, so test book, there are many test book. One very good test book, it is called the Kane and Hamler. That is actually one book from the data mining field. You can find a good discussion. Another good book is Nan, Tan and Vapnik. Vapnik itself written one good book. So these two books are very popular and very nicely written. Anyone can follow it. Okay, I'll send, okay, right now I'm not able to write the name of the book, but anyway, so Hans and Kamler, it is the one book, and Nan Ping Tang and Vapinik is the another book. It is a Vipin Kumar and Vapnik, one professor from IIT Kanpur, also co-author of that book. These are the two books are very good. You can get the search, you can find it. The two books on very SBM, and a lot of materials you can find from the internet, and then okay, white paper are there which can discuss. There are many even in the Python like code also available with some data available, so that how SBM can be learned from the input data, everything is available. So rich source of information you can find the internet itself. Now here, yes, so there is one question, sir. I implemented logistic discrimination analysis SBM on same data having 8 dimensions, but I got SBM accuracy less than other two. What we can infer? I'm telling you. Now this actually is supposed to be that that LDA gives poor result compared to SBM, but sometimes LDA gives better result depending on. Actually, if your data is not balanced, right, or if your data is too much, not too much linearly, okay, too much non-linearly rather distributed, then definitely LDA will give better result than the SBM. But this is a rare situation. Usually LDA and SBM are comparable. So if SBM give good result, LDA is supposed to give good result. If SBM does not give, LDA does not give. So you may probably, that is what I'm guessing, but if I see the data and then I can tell it, that accuracy may be not so much good for SBM due to insufficient amount of training data set, or maybe too much noise in your data set, or maybe that coincidental, that LDA surprisingly give result. So that maybe many reasons are there. So unless if we examine the data directly, then it is not possible to tell it about it. Okay, and few okay questions. I think it is not linked to me. And here, okay, you want to have some. Okay, just a minute, please. So you want to know some data from the chat box. Okay, I'm typing the name. Here is actually data mining. It is a good book by and so it is a one good book. This book from Morgan Kaufman book, very good book. Another good book from Addison Wesley. This book is from Nan Ping Vapnik and Vipin Kumar. Right? This is a one book, also you can take it. Right? So this is also the title is Introduction to Machine Learning. Introduction to Machine Learning. So these are the mainly two books that you can think. One is GUI hand, so it is not HZN, so typing mistake HAN. Okay, so these are the books that you can find about it, and then these are good books. Now, introduction to machine learning. Now, other than accuracy, which measures can be considered to describe SVM result? Is a very good question. Thank you. I'm telling you, the accuracy of a classification technique can be measured using many metrics other than accuracy. Accuracy is very simple estimation. Accuracy means how many of the data has been predicted correctly divided by total number of data. So the numerator by denominator. But there are many other metrics available in the machine learning book. One measurement, it is called the precision. Another is called the recall, and then F1 score. So there are some metrics actually, precision and recall, they measure in terms of type 1 error and type 2 error. What is the type 1 error? There are some data which are true but predicted as false. So this is an error. Some data which is false but predicted as true. This is also an error. So previously it is called the type 1 error and it is called the type 2 error. So if we want to stress on type 1 error, then the measurement recall. And if you want to emphasize on precision, then it is called the type 2 error, then it is precision. F1 score actually gives the both measure type 1 type 2 error into account. So these are the another metrics. Other than these precision, recall and F1 score, there is also one metric is called the loss function. So loss function actually based on the error. The error can be estimated. So how many, say suppose you have predicted one data which is very close to the actual data, actual output. Then I told you that very close. How you can measure this closeness of the data? For example, there is a data, it is called V, and another is U. So your model predicted U instead of V. But it is similarity of V and U if you see, and if you consider the image of the V and U, then you can find how much. So error can be calculated by means of this one. And this kind of error calculation, it is called the loss function. So how much loss that you can have, so far the prediction is there. So idea is that there is a validation technique. There are many validation technique called k-fold validation, and then Monte Carlo validation. So many validation techniques are there, using which you can calculate the loss function and also all those metrics measurement like precision, recall and F1 score that you can use it. Okay, so these are the different metrics that you can think for calculating the accuracy or performance of a classification technique. Okay, now what I can do is I can the slide that I have used for this presentation, as you are teacher, right, these slides will be helpful for you to understand because these are one-way communication. But if you have the slide, you can go through the slide according to your own space, and at the end of the slide I will give you some network link as well as some textbook. Those are very good according to my study, so that you can go through and then you can use it. You can help, okay, which if it can help you for your teaching endeavor, then it will be very good. So I'll send the slide, I'll send it to Professor Devangan, so he will forward the slides to all of you so that you can utilize this one. Okay, so I'll share it by today evening. Professor Devangan, I'll share it to him and then he will forward to all of you. So one question from Aparna. No, not Aparna, from Dilkesh. Is it possible accuracy of one model less than other? Recall and precision can better. Actually, see, depends on. Everything is possible. That is why we have to test. So usually whenever we test our result, then usually I ask my student that test with all classification technique, including random forest, ensemble classification, whatever it is there. But the result that can be obtained, it depends on, data distribution, what sort of there. So usually in majority of the cases, SVM give better result. But in some situation, it is observed that, for example, your data is with categorical data, that Bayesian classification give better result. So it depends on, you cannot tell that way how you. Now, for example, SVM not guaranteed to give you better result because the kernel that you have chosen not correctly, wrongly. So those are the deciding factor actually, that accuracy, even with the SVM, it may not give good result because there are so many, there is a scope of holes actually, so that you have to be a little bit careful about it. That is why all the algorithms available as a built-in code, maybe Python, scikit, and so many other tools are available, even in the MATLAB. So you don't have to write much program. Only the thing is that you apply your data with all techniques and then get the result, and then do all sort of experiment. It is basically empirical study look like, and then ultimately get the conclusion that okay, this is the accuracy with this technique, and this is the highest accuracy that you get. So it is actually data centric. All this, that is why it is actually a concept of data science. Yeah, I don't have PPT. I have only PDF file. Actually, I made it on the LaTeX only, so I forward the PDF file only to you. Yes. So Python, Skylern you can take, or there are many other scikit or many other libraries available. You can take and then you can check. Good. Okay, fine. So, okay, with this, I would like to conclude our presentation here today. So finally, I'll forward the slides and then links and then other textbooks so that you can go through. That can help you to learn it, right? That's fine then.
Thank you so much, sir. Thank you so much for sharing your enlightening lecture on SVM and its application, and especially for your time you have given to our institute. And I hope all the participants have cleared their doubts.
Okay, thank you all. Okay, take care. Wish you
Thank
all
you,
the
sir.
best. Okay,
Thank you,
I'm now
sir.
leaving then.
Okay, sir. Thank you, sir. For participants, please give your feedback and also attend the quiz. Link is active now for another 5 to 10 minutes. Please give your feedback fast and attend the quiz also. Our next session will be from 2:30 p.m. There is a lunch break of almost 1 hour. We will rejoin at 2:30 p.m. Thank you so much.